Today's lecture is how the Schrödinger equation was discovered. Think about a simple hydrogen atom, just one proton in the middle and one electron buzzing around it. Back in the early part of the 20th century, this was a real problem. We knew the electron was there. We knew it had a negative charge. We knew the proton had a positive charge, and we knew that opposite charges attract. If you put a charge near another, they pull together. If you just leave them alone, the electron should spiral right into the proton. It should crash, or everything should collapse, but it didn't. Atoms were stable. They sat there. The universe didn't fall apart. Niels Bohr had an idea. He said maybe the electron can only be in certain orbits, like rungs on a ladder. You can stand on the first rung or the second, but you can't stand in between. It was a rule, a postulate. It worked to explain the lines of light you saw coming off hydrogen, but it felt funny. It didn't feel like physics. It felt like a rule someone invented just to make the math come out right. It wasn't derived from anything deeper. It was just a patch. Then came Louis de Broglie. He was a student, and he had a thought. He asked himself, if light can act like a particle, why can't a particle act like a wave? We were used to light being a wave. We were used to electrons being little hard balls of matter. De Broglie said, no, maybe the electron has a wavelength. He even wrote down a formula for it. It depended on the momentum, a simple little relation. Now take that idea. If the electron is a wave, then Bohr's rungs on the ladder start to make sense. A wave on a guitar string can only vibrate at certain frequencies. You pluck it and it rings at one pitch. You put your finger down, you change the length, it rings at another pitch. You can't get it to ring just any old way. The wave has to fit. It has to close on itself. If the electron is a wave going around the nucleus, it has to fit perfectly in its orbit. If the circumference isn't a multiple of the wavelength, the wave interferes with itself and dies out. That's why you have fixed orbits. It's like a standing wave on a string. Erwin Schrödinger heard about this. He was a physicist working in Switzerland. He had a background in general relativity, which used to be fancy differential equations. He was smart. He looked at this idea, the electron is a wave, and he thought, if it's a wave, it must have a wave equation. That's how physics works. Sometimes, if you have a wave, a sound wave, a water wave, a light wave, you have an equation that describes how that wave moves and changes. You have a wave equation. Schrödinger didn't just guess the equation. Well, he did in a way, but it was an educated guess based on what he knew about classical mechanics. He knew about Hamilton's formulation of mechanics. Hamilton had this way of looking at motion. Instead of just forces and accelerations, you look at energy. You have an energy function, the Hamiltonian. It tells you the total energy of a system, kinetic plus potential. Schrödinger asked himself, can I connect the wave aspect of the electron to the energy of the electron? He looked at the Hamilton-Jacobi equation. That's a classic tool. It describes how an action function evolves in time. It's very abstract, very mathematical. Schrödinger looked at that and said, if I treat the action as the phase of a wave, maybe I can turn this classical mechanics equation into a wave equation. He tried it. He sat down and wrote it out. He wanted a relationship between the energy and the geometry of the wave. He played with the variables. He looked at the requirement that the wave had to be continuous. It had to be smooth. If you have a wave, you don't want it snapping or breaking. It has to exist in a way that respects the boundary conditions of the atom. The first attempt he made, it was actually for a relativistic case. He assumed the electron was moving at speeds close to light. He wrote down the equation. He checked it against the hydrogen atom. It didn't work. It gave the wrong energy levels. He was disappointed. He put it away. He thought he was wrong. Most people would stop there. They would say, well, the idea is wrong. Electrons aren't wave. Let's try something else. Schrödinger didn't do that. He kept the idea in the back of his mind. He went on a ski trip. He took a girlfriend with him. He had time to think. He kept coming back to the wave idea. He decided to try the non-relativistic case, ignore the speed of light, and just treat it as a slower, simpler system. He went back to the drawing board. He took the non-relativistic energy equation. Kinetic energy is just momentum squared divided by 2 times the mass, plus potential energy. He turned that into an operator equation. He replaced momentum with a gradient, a derivative, but it's a trick. In quantum mechanics, we replace quantities with operations. Momentum becomes a way of taking a derivative of the wave function. Energy becomes a way of taking a derivative with respect to time. He wrote down the equation. It looked nice. It was a partial differential equation that described the field. He solved it for the hydrogen atom. He found the energy levels that they matched Bohr's results exactly, the spectrum of hydrogen. Everything clicked. The standing wave idea was validated by the math. It was a beautiful moment. But here's the thing that people often miss. Schrödinger didn't think the electron was a physical wave of matter. He thought the electron was a cloud of charge. He thought the wave function was the electron, that the density of the charge was proportional to the square of the amplitude of the wave. He was wrong about that. We know that now, but his equation was right. This is a common pattern in physics, and you find an equation that works, but your interpretation of what it means is slightly off. You think you're describing one thing, but you're actually describing something deeper. Max Born came along a bit later and said, wait a minute, that wave function isn't a physical density of charge, it's a probability amplitude. If you want to know where the electron is, you take the wave function, you square it, and that tells you the probability of finding the electron at a certain spot. It doesn't tell you where the electron is. It tells you where you are likely to find it if you look. This was a shift. It changed everything, but Schrödinger hated it. He really didn't like the idea of probability at the heart of nature. He liked continuous, smooth fields. He wanted nature to be deterministic, but the math held up. The equation predicted things. It predicted the behavior of atoms, the way they bond, the way they reflect light. It was precise. It was correct. So how do we use this equation? What does it actually look like? It's not just a set of symbols. It's a way to calculate the future state of a system. If you know the present state, you have the wave function. You apply the Hamiltonian, which is the operator for total energy, and it tells you how that wave function changes as time moves forward. It's linear. That's important. If you have 2 possible states for the system, you can add them together, and that's also a possible state. You can have the electron here, and you can have it there, and the superposition is the electron being in both places at once until you measure it. That's the spooky part. It's not actually spooky if you just accept that the wave function describes what we know or what we can calculate about the system. I want you to think about how this changes our view of an atom. Before, we had little planets orbiting a sun, little circles, hard paths. Now we have a cloud, a smear of probability. The electron isn't at a point. It's distributed. When we say the electron is here, we mean we have a high probability of finding it here. It's a different way of seeing reality. It's not just about atoms, and it's about anything that behaves like a wave. Molecules, crystals, even the whole universe, if you want to push it that far. The Schrödinger equation is the foundation for almost all of chemistry. Every bond, every reaction, every interaction between atoms, it's all governed by this equation. It's the rule book for the microscopic world. Now, let's look at the difficulty. Solving this equation is hard. For a hydrogen atom, it's fine. You can do it with pencil and paper. For a helium atom with 2 electrons, it's tough. Those 2 electrons interact with each other. They repel each other. You have to account for that. You have to include an interaction term. The equation becomes coupled. You can't separate it easily. You have to use approximations, so you have to guess. This is the reality of physics. We have a fundamental equation, the Schrödinger equation, which we believe is correct, but we can't solve it exactly for most systems. We don't have a computer big enough to calculate the exact wave function for a complex molecule. So we do perturbation theory. We start with a simple system we can solve, and we add little corrections to account for the complication, and we build up the solution piece by piece. It's honest work. It's not elegant, maybe, but it worked. You take the hydrogen solution and you add a little bit of the interaction energy. You check your work. You compare it to the experiment. If it matches, you're on the right track. If it doesn't, you go back. You refine your approximation. There's a lesson in this. Don't get hung up on needing the perfect exact solution immediately. Physics is about approximation. It's about peeling an onion. You get one layer, then you go deeper. You find a new complexity, you deal with it, and you go deeper still. Why did Schrödinger succeed when others didn't? He was persistent. He didn't just give up when his first attempt failed. He had a strong physical intuition. He knew that the wave-particle duality was the key, even if he didn't fully understand what the wave represented. He trusted the math. He trusted the structure of the classical equations he was modifying. There's a story I like. Maybe it's apocryphal, but it illustrates the point about Schrödinger presenting his work. Someone asked him, but what is the wave vibrating in? And he didn't have a good answer, because it wasn't vibrating in space like a guitar string. It was a wave in configuration space, a mathematical space. That's a hard thing to wrap your head around. If you have a system with n particles, the configuration space has 3 n dimensions. That's a lot of dimension. A wave moving in 3 n dimensions is not something you can visualize it, but you can calculate it. Don't try to visualize it. That's a mistake people make. They want to draw a picture. They want to see the little wave bobbing up and down. You can't see it. It's not in the physical 3-dimensional space we live in. It's an abstract mathematical object. It's a tool. It's the best tool we have, but it's a tool. So when you study this, don't ask, what does it look like? Ask, what does it predict? That's the question that matters. Does it predict the energy levels? Yes. Does it predict the transition rates? Yes. Does it predict the shape of the molecule? Yes. That's enough. I remember when I was learning this, I had trouble with the concept of the operator. Why turn momentum into a derivative? It seemed like a trick. But then I realized that in the world of quantum mechanics, these variables aren't just numbers. They are generators of change. Momentum generates translation. Energy generates time evolution. That's the deep connection. Once you see that, the math makes sense. It's not just a collection of rules, it's a structure of symmetry. Everything in nature has symmetries. If you shift your experiment over by a foot, nothing changes. That's translation symmetry. Momentum is the conserved quantity associated with that symmetry. If you wait a minute, nothing changes. That's time symmetry. Energy is the conserved quantity for that. Schrödinger's equation is just the statement of how these symmetries play out in a quantum system. It's elegant, really. It's not just a bunch of scribbles on a board. It's a deep reflection of the way the universe is built. Now, let's think about the limitations. We've been talking about the Schrödinger equation, but this is non-relativistic. It's for particles moving slowly to us. What about particles moving fast near the speed of light? The Schrödinger equation breaks down. You need something else. You need the Dirac equation that incorporates special relativity. It predicts antimatter. It's a whole different level of complexity. But for most chemistry, for most of the stuff we do here, the Schrödinger equation is enough. It's like using Newtonian mechanics to build a bridge. You don't need general relativity to understand how a bridge stands up. You don't need the Dirac equation to understand how a water molecule holds together. You use the right tool for the job. I often see students get stuck because they try to understand the why before they understand the how. They want to know why nature is this way and why is the electron a wave? Why is it probability? I don't know why nature is just that way, like we didn't invent it. We discovered it. The job of the physicist is to describe what is, not to say what should be. If the equation works, you use it. If it doesn't, you find a better one. That's the game. It's a game of guessing, checking, and refining. You guess an equation. You check it against reality. If it matches, great. If not, throw it out. Schrödinger guessed. He checked. It matched. That's the story. It wasn't a divine revelation. It was a lot of hard work, a lot of failure, and a bit of luck. Let's look at the equation itself, just to be sure we have the structure. You have the wave function. Let's call it psi. The Schrödinger equation says that the time derivative of psi multiplied by h bar and an imaginary number is equal to the Hamiltonian acting on psi. That's it. That's the whole thing. It's linear. The derivative is linear. The Hamiltonian is linear. That's why it's so powerful. You can add solution. You can have interference. You can have patterns. It explains why you get bright and dark spots in a diffraction experiment. It explains why you get the patterns you see in crystals. It's all interference of the wave function. Think about the double slit experiment. You shoot electrons at a screen with two slits. If they were little balls, you get two humps of electrons, but you don't. You get an interference pattern, a series of bright and dark stripes. That's exactly what a wave does. It goes through both slits, interferes with itself, and creates the pattern. The Schrödinger equation describes exactly that. It calculates the amplitude of the wave at every point on the screen. The square of that amplitude is the probability of the electron hitting that spot. It works perfectly. It's one of the most successful theories in the history of science. It's never been proven wrong. Every experiment we've done to test it has confirmed it. It's solid. But it's also weird. It forces us to accept that the world at the bottom level is not certain. It's a world of possibilities. We calculate the likelihood of an event, not the event itself. But some people find that disturbing, and they want to know the real path of the electron. But there is no path, and that's the point. The concept of a path is a classical idea. It belongs to the world of billiard balls and planets. It doesn't apply to the world of atoms. You have to let go of the idea of a path. You have to accept the wave function. That's what it is. It's the complete description of the state of the system. Everything you can possibly know about the system is contained in the wave function. You can't know more than that. If you know the wave function, you know everything that can be known. That's a radical thought. It means there's a limit to knowledge. We can't know where the electron is and how fast it's going at the same time. The more you know about one, the less you know about the other. That's the uncertainty principle. And it falls right out of the Schrödinger equation. It's a mathematical consequence of the wave nature of the electron. If you want to define the position of a wave, you have to localize it. To localize a wave, you have to combine many different wavelengths. That means you have a range of momenta. So you lose precision in momentum. It's not an experimental error. It's not that our instruments aren't good enough. It's a fundamental property of the universe. It's a trade-off. Nature is built on trade-off. You want certainty. You can't have it. You want precision, and you have to pay for it. The universe is not a clockwork machine. It's more like a fuzzy, shimmering web of possibilities. And we are just observing it, trying to map out the rules. When you look at this, you might feel a bit lost, and that's okay. I felt lost too, so it took me a long time to get comfortable with this way of thinking. You spend your whole life in the world of classical mechanics where things are predictable, where you can follow a ball in flight, a car. Then you step into the world of atoms and everything you know about motion goes out the window. It's disorienting. But keep at it. Don't try to force it into a classical mold. Don't say it's like a wave, but really it's a particle. That leads to confusion. Just say it's a quantum object. It has properties of both, but it is neither. It's its own thing. It obeys its own rules. The Schrödinger equation is the rule book. Let's re-examine the Hamiltonian. It's the key. If you want to solve a new problem, say a molecule with a new geometry, you where you don't write a new Schrödinger equation. You write a new Hamiltonian and you put in the new potential energy, the new interactions, and you use the same equation. You just plug it into the operator. It's a very general framework. What about time? The Schrödinger equation is time dependent. It tells you how the state changes. But what about systems that are in a steady state? Atoms, for example, and they don't change over time. The electron is just there in its orbit. For those cases, we use the time-independent Schrödinger equation. It's an eigenvalue problem. You are looking for the stationary states, the states where the probability doesn't change over time. It's just a different way of using the same equation. It's like asking, what are the natural frequencies of this bridge? You ignore the time and you look for the modes of vibration. It's the same physics. I remember once I was trying to explain this to someone and they asked, but what if the electron changes state? What if it drops from a high energy level to a low one? The Schrödinger equation doesn't explain that by itself. That's a transition, and that requires an interaction with the electromagnetic field. It requires quantum electrodynamics. That's a step further. We have to add the field to the equation. But the core, the idea that the electron state is a wave function that changes according to a Hamiltonian, that remains. It's a foundation. You can build a skyscraper on it, a quantum chemistry, solid state physics, materials science, it all rests on this. Transistors, computers, lasers, they all now work because we understand how the wave function behaves. We manipulate the wave functions to make the electronics work. We force the electrons into the states we want. We make them do what we need. It's remarkable that a few lines of math derived by a guy on a vacation can change the entire course of technology. Now, let's think about the math again. Is it just magic? No, it's a transformation. You take the classical energy equation and you transform it into an operator equation. Why does that work? That's the deep mystery. Why is nature quantum? Why is there a wave function at all? Maybe it's just the simplest way to describe a system that has a fundamental limit on how much you can know. If you have a system where you can't have perfect knowledge of position and momentum, the wave function is the most efficient way to store the information you do have. Think of it as a bookkeeping system. You have to keep track of what you know. You can't track position. So you track the wave function. It contains the maximum amount of information allowed by the universe. That's a nice way to think about it. It's not about waves and particles. It's about information. The wave function is just the state of our knowledge about the system. When we make a measurement, the wave function collapses, or as I prefer to think, we update our information. We get a result and we adjust our knowledge to match the result. This interpretation, the idea that the wave function is information, helps clear up a lot of the confusion. It stops you from asking, where is the electron really? There is no really. There is only the result of the measurement. The wave function is just the tool we use to predict the probability of that result. I know, it sounds like a cop-out. You want to know what's happening under the hood. But that's the thing, there is no hood. There is just the observation. That's the lesson of quantum mechanics that comes. Reality is what we observe. The rest is just math. Now let's talk about the complexity of the wave function. It's a complex number. It has a real part and an imaginary part. Why complex? Why not just real? Because you need the phase. You need the phase to describe interference. If you just had real numbers, you couldn't describe the shift in the waves. You couldn't describe the interference patterns. And you need the imaginary unit. It's not just a mathematical convenience, it's essential. Without I, the equation doesn't work. It's amazing that nature requires imaginary numbers. You think of imaginary numbers as something you learn in school, some abstract invention. But here they are, at the heart of the universe. They are necessary to describe the way the world works. When I look at the Schrödinger equation, I don't see symbols, just survey. I see the heartbeat of the atom. I see the potential, the kinetic energy, the probability, the interference. It's all there. packed into a single compact equation. It's beautiful. Do you have any questions about this part? I know it's a lot to take in. It's a big shift in how you think about nature. It's supposed to be confusing. If you're not confused, you haven't understood it. Let's go back to the beginning, the discovery. Schrödinger didn't set out to create a new paradigm. He just wanted to solve the atom problem, and he was an engineer of physics in a way. He had a problem, the hydrogen atom, and he looked for a solution. He found the wave equation. He wasn't trying to be a philosopher, and he was just doing his job. And that's the best way to do science. Don't try to be a philosopher. Don't try to solve the meaning of life. Just solve the problem in front of you. The meaning will take care of itself. If Schrödinger had sat around wondering if he was transforming the scientific landscape, he never would have written the equation. He would have been too busy writing speeches. Instead, he just did the math. He went to work. That's what I admire about him, the focus, the simplicity. He didn't use big words, and he didn't talk about the essence of reality. He talked about eigenvalues. He talked about boundary conditions. That's the language of a physicist. It's concrete. It's specific. Let's look at the hydrogen atom again. You have the potential energy, 1 over ρ. That's the Coulomb potential. You put that into the Schrödinger equation. You solve for the radial part and the angular part. The angular part gives you spherical harmonic buzz. Those are the shapes of the electron cloud. The s orbital is a sphere. The p orbital is a dumbbell. It's beautiful geometry. It's not just math, it's visual. If you can see the shapes, you can see why molecules form the way they do. The shapes dictate the bonds dictate the chemistry dictates the light. It's all connected. It all starts with the Schrödinger equation. I think the biggest mistake people make when they learn this is they think it's finished. They think, okay, we have the equation, now we understand everything. But we don't. We have the equation, but we don't understand the system. We don't understand the complexity that emerges from the equation. We don't understand why a protein folds the way it does, even though the Schrödinger equation describes every atom in the protein. We can't solve it for that many atoms. There's a huge gap between the fundamental equation and the real-world behavior. That's where the work is. That's where the fun is. You have the rules, the Schrödinger equation, but you still have to play the game. You have to figure out how the rules apply to the complex, messy systems we see around us. And that's the real frontier. It's not in refining the equation. It's in applying it to bigger and bigger systems. It's in understanding emergent behavior. It's in seeing how the quantum world builds the classical world. I sometimes wonder what Schrödinger would think of what we've done with his equation. I think he'd be surprised. He'd be surprised that we can calculate the properties of a silicon chip. He'd be surprised that we can simulate a chemical reaction on a computer. He'd be amazed at the precision of the results, but I think he'd also be humble. He'd say, well, it's just an equation. It's a tool. It works. He wasn't a man for grand statements, Lee. He was a man for precise solutions. And that's what we need more of. Not more grand statements, but more precise solutions. So let's think about the future. What's next? We have the Schrödinger equation. We have the Dirac equation. We have quantum field theory. We're pushing into smaller and smaller scales. We're looking for the theory of everything. We're looking for a way to combine gravity with the quantum rules. That's the big problem. The Schrödinger equation doesn't include gravity. General relativity is a theory of geometry. Quantum mechanics is a theory of waves. How do you combine them? How do you quantize gravity? That's the question of our time. And maybe, just maybe, the answer will come from the same kind of thinking Schrödinger used. A guess, an intuition, a bridge between two different ways of looking at the world. Maybe we need a new Hamiltonian. Maybe we need a new way to describe space-time. I don't know. But I know that the way to find it is to keep working on the problem, to keep looking at the data, to keep trusting the math even when it feels weird, because that's how it works. But you follow the math and it leads you to places you didn't expect. It leads you to new truths. It leads you to a better understanding of the universe. And it's a beautiful journey. It's not a straight line. It's a messy, winding path. You make mistakes. You get lost. You have to turn back. But you keep going. You keep exploring. And every once in a while, you find something that changes everything. You find a piece of the puzzle. You find a new layer of the onion. That's science, ain't it, sir? It's not a collection of facts. It's an activity. It's a way of looking at the world. And the Schrödinger equation is one of the best examples of that activity in action. It's a testament to the power of the human mind to grasp the rules of the universe using nothing but logic, intuition, and a bit of chalk and a blackboard. I often think about the day Schrödinger wrote that equation. He was sitting in his room looking at the problem. And then he wasn't thinking about fame. He wasn't thinking about the Nobel Prize. He was thinking about the hydrogen atom. He was thinking about the wave. He was thinking about the math. And in that moment, he connected with the fundamental structure of reality. He didn't invent the equation. He discovered it. It was already there, hidden in the structure of the universe, waiting for someone to find it. He just happened to be the one who looked in the right place. And that's the joy of physics. You're not inventing things. You're uncovering what's already there. You're peeling back the veil. You're getting a glimpse of the machinery underneath. It's a privilege, really, to be able to understand the world in this way, to be able to see the patterns, the symmetries, the beauty of the math. It's the closest we get to seeing the mind of the Creator, or the nature of the universe, whatever you want to call it. So don't just memorize the equation. Don't just learn how to solve the problems for the exam. Try to understand the why. Try to feel the intuition. Try to see the connection between the classical world and the quantum world. Try to see the beauty of the math. If you can do that, you'll have a much deeper understanding of what physics is all about. You'll have a much deeper appreciation for what Schrödinger did. And maybe, just maybe, you'll be the one to find the next piece of the puzzle. You have the tools. You have the knowledge. You have the curiosity. That's all you need. The rest is just work. And the work is worth it. It's worth it to know. It's worth it to understand. Oh, it's worth it to be part of this great adventure. Let's stop here for a moment. Are there any parts of this that don't sit right with you? Any parts that feel like a stretch? Because that's where the real learning happens. When you hit a wall, when you find a place where the logic doesn't hold together, that's where you have to dig in. That's where you have to think harder. Don't ignore the confusion. Lean into it. That's the sign that you're on the edge of a discovery. Think about the wave function as a probability amplitude again. Is that satisfying? Does it feel real? Or does it feel like a trick? If it feels like a trick, that's good. That's healthy skepticism. But don't let the skepticism stop you from using it. Use it, test it, push it. See where it breaks. See if you can find a better way. Maybe you'll be the one to rewrite the interpretation. Maybe you'll be the one to make it clearer. That's the history of science. It's one generation building on the next, refining, improving, clarifying. We have the Schrödinger equation now, but maybe in 50 years, we'll have something even better. Something that makes the wave function obsolete. Something that explains the universe in a way that's even more elegant, even more powerful. That's the beauty of it. It's never done. It's always evolving. It's always growing, and you're part of that. You're part of the process. So what are you going to do with it? Are you going to just learn it, or are you going to use it? Are you going to apply it? Are you going to question it? That's up to you, but I hope you do something with it. I hope you take it and run with it, because it's a powerful tool, and we need more people who know how to use it. We need more people who can see the world through the lens of the Schrödinger equation. We need more people who can appreciate the beauty of the math. We need more people who can solve the problems that matter. So take this. It's yours now. It's a gift from Schrödinger and from the generations of physicists who have worked on it. It's a piece of the truth. Use it well. I want to leave you with one final thought. The Schrödinger equation is not just a bunch of math. It's a story. It's a story about the electron. It's a story about the atom. It's a story about the way the universe works. And you're part of that story. You're the next chapter. What are you going to write? What are you going to discover? That's the question. That's the challenge. And it's an exciting one. So go ahead. Get to work. Don't wait for permission. Don't wait for the right moment. The moment is now. The problem is waiting. The universe is waiting. Go and see what you can find. I remember my own struggles with this. I had a hard time with the formalism, the bracket notation, the Hilbert spaces. It felt like a language I didn't speak, but I kept at it. I wrote down the equations. I played with them. I looked for patterns, and slowly it started to make sense. It started to speak to me. That's the key. You have to speak the language. And the only way to do that is to practice, to work the problem, to write the equations, to make them your own. Don't be intimidated by the math. It's just a language. It's the language of nature, and you can learn it. You can master it. You can use it to talk to the universe. And isn't that a wonderful thought? To be able to ask the universe a question and to get an answer in its own language. That's what physics is. That's what it means to be a scientist. So keep studying. Keep asking questions. Keep pushing the boundaries, and never lose your curiosity. That's the most important thing. The curiosity is what drives it all. It's what keeps you going when the math gets tough. It's what makes it all worthwhile. I'm looking forward to seeing what you come up with. I'm looking forward to seeing where you take this. I'm looking forward to seeing what the next chapter of the story looks like. And remember, it's not about being right. It's about being curious. It's about being honest. It's about being real. It's about looking at the world as it is, not as you want it to be. That's the lesson I learned from Schrödinger. That's the lesson I'm trying to pass on to you. Be honest with the math. Be honest with the data. Be honest with yourself. And if you do that, you'll be in good company. You'll be part of the great tradition of physics. You'll be part of the search for truth. And that's a good place to be. I think we've covered enough for today. We've talked about the background, the struggle, the breakthrough, the interpretation, and the significance. We've looked at the equation, the math, and the implication. We've explored the history and the future. It's been a good session. I hope you got something out of it. I hope it made you think. I hope it sparked something in you. If you have any lingering doubts, any questions that keep you up at night, write them down. Keep them with you. That's where the real work happened. That's where the discoveries are waiting. The Schrödinger equation is just the beginning. It's a door. It's a gate. It's a key. What you do with it is up to you. Open the door. Walk through. See what's on the other side. That's the best advice I can give you. And remember, physics is not about what we know. It's about what we don't know. It's about the questions, not the answers. It's about the journey, not the destination. Enjoy the journey. Thank you. Today's lecture is how the Planck constant was discovered. Let's start with a stove. You have a heating element, the kind that turns bright red when you crank the dial up. You've seen this 1,000 times. You turn it on, the wire starts to glow. It gets hotter and the color shifts. It goes from a dull red to a brighter red, and if you could get it hot enough, which you can't with a standard kitchen stove without melting the whole thing, it would turn orange, yellow, then white. It's light. But why? Why does the thing glowing? We call it a black body in physics. Just a fancy name for an object that absorbs and emits radiation perfectly? Change color? It's not just a matter of getting hotter. There's a rule here, a specific relationship between the heat of the object and the color of the light and it spits out. Back in the late 1800s, this was the big question. It wasn't some abstract, high-flying philosophy. It was a practical, nagging problem that kept the best physicists awake at night. They wanted to know the exact shape of the curve. If you plot the intensity of the light on one axis and the frequency on the other, you get a hump, a smooth, rounded shape. At low temperatures, the hump is way over to the left. At low frequencies, infrared mostly, which we feel as heat. As you crank the temperature up, the hump shifts to the right into the visible spectrum. The problem was that the classical laws of physics, the ones we knew and trusted, and the ones that worked for planets and bridges and steam engines, couldn't predict this curve. They failed. And they didn't just fail a little bit. They failed spectacularly. Let's look at the two big ideas they had at the time. First, you had Wilhelm Wien. He had a formula that worked great for the high-frequency end of the curve. If you looked at the blue light, the ultraviolet side, Wien's law fit the data like a glove, but it completely missed the mark when you looked at the low-frequency side. Then you had Lord Rayleigh and James Jeans. Their approach, which used the standard statistical mechanics of the time, was perfect for the low frequencies, the infrared stuff, but it went absolutely haywire at the high end. That's where the trouble started. The Rayleigh-Jeans law predicted that as you move to higher frequencies, the intensity of the radiation should keep going up and up and up to infinity. Think about that for a second. If that law were true, every time you turned on a lamp, you'd be blasted by an infinite amount of ultraviolet light, X-rays, and gamma rays. You'd be incinerated. The room would be filled with infinite energy. It's what we call the ultraviolet catastrophe. Obviously, that doesn't happen. You turn on a light bulb, the room gets warm, you can read your book, and you don't die. So the theory was wrong. The math was solid. They hadn't made a mistake in the calculation, but the starting assumptions about how energy behaves were clearly busted. Max Planck was working on this in Berlin. He was a conservative guy, not the type to go around burning down the establishment. He liked thermodynamics. He liked the solid, established rules of energy. He wasn't trying to invent a new universe. He was trying to solve a puzzle. He wanted to find a formula that connected the two ends of the curve, the Wien side and the Rayleigh-Jeans side. He wanted a single equation that would describe the hump perfectly. He tried everything. He looked at the data coming out of the labs. People like Rubens and Kurlbaum were doing careful measurements of blackbody radiation, and they had these precise, beautiful curves. Planck stared at these curves. He wanted to interpolate. He wanted to find a mathematical function that, when the frequency was low, acted like the Rayleigh-Jeans law, and when the frequency was high, acted like the Wien law. It's like trying to draw a smooth line through a set of points where you have two different maps for the start and the end. Then you need to figure out the path in the middle. He messed with the exponents. Ooh. He added constants as he tweaked the variables. He wasn't thinking about quantum anything. He was just doing algebra. He was playing with the math until it fit the data points out. And one evening in October 1900, he found it. He hit on an equation. It fit the data perfectly, not mostly, not approximately. Perfectly, as all the points lay right on the line. He sent this equation to his colleagues, and they checked it. It worked. It was an empirical success. But Planck was unhappy. He had the what, but he didn't have the why. Why did the specific mathematical function describe nature? What was going on underneath the hood? That's the moment the real work begins. He had to figure out the physical mechanism that would produce this formula. He started by looking at how oscillators, tiny hypothetical vibrating charges inside the walls of the black body, interacted with the radiation. He had to calculate the entropy of these oscillators. It's a messy calculation. You have to count the number of ways to distribute energy among these oscillators. In the classical world, the world of Newton, the world of things we can see and touch, energy is continuous. You have a ball. You push it, it has some energy. You push it harder, it has more energy. You can change that energy by any amount, no matter how small. It's like a ramp. You can stand anywhere on a ramp. But to make his formula work, to make the math match the data, Planck had to do something strange. He had to assume that the oscillators could only exchange energy in specific discrete chunks. Imagine a ramp, but you can stand anywhere. Now imagine a staircase. You can only stand on a step. You can't stand between the steps. Planck had to assume that the energy of these oscillators was proportional to their frequency. Specifically, that the energy was equal to a number, a constant, multiplied by the frequency. Energy equals Planck's constant times frequency. He called this constant Planck's constant, represented by the letter h. He didn't think Planck's constant was a fundamental property of the universe. He thought it was a mathematical trick, a temporary scaffolding he could take down once he figured out the real physics. He hoped that if he looked long enough, he'd find a way to let Planck's constant go to zero, turning the staircase back into a ramp. But the more he worked on it, the more he realized he couldn't get rid of it. The constant was stuck. It was there to stay. Think about why this is such a shock. If energy comes in chunks, in quanta as we call them, then the world isn't continuous at the bottom, it's granular. But why? Why should nature be so picky about how much energy it accepts? Planck didn't know. He struggled with this for years. He tried to reconcile it with classical physics, but the gap was too wide. He had unknowingly started a fire. He had introduced the idea that energy is not a fluid, but a pile of grains. Let's step back. Why does this matter? Because before this, physics was about determinism. If you knew where a particle was and how fast it was moving, you knew everything. The future was just a calculation load. But once you introduce these discrete chunks, you realize that the interaction between light and matter is not a smooth, continuous exchange. It's a series of collisions, of exchanges of packets. It's like money. You can think of energy as fluid, like water. But if you look closely enough, you realize it's actually made of pennies. You can't have half a penny. You can have 1 or 2 or 10, but never 1.5. In the macroscopic world, the pennies are so small that it looks like a fluid. You don't notice the graininess, but in the microscopic world, the pennies are huge compared to the transaction. That's the quantum level. Planck realized that for his formula to work, these pennies of energy, these quanta, had to be proportional to the frequency of the light. High-frequency light, like ultraviolet, has big quanta. Low-frequency light, like infrared, has small quanta. Now consider the ultraviolet catastrophe again. Why did the old theory fail? Because it assumed you could have an infinite number of these oscillators vibrating at any frequency, and they could all have tiny, tiny amounts of energy, effectively giving you an infinite supply of states for the high frequencies. But Planck's idea said, wait, to get a high frequency vibration, you need a big chunk of energy. If you don't have enough energy to pay for that big chunk, that vibration simply doesn't happen. It's frozen out. It's too expensive. The high frequency states are suppressed. They are improbable. And that stops the energy from going to infinity. The curve turns over and drops to zero. The catastrophe is avoided, not because of a complicated new force, but because the universe demands a minimum payment, a quantum, for energy exchange at high frequencies. It's such a simple, elegant solution. And yet Planck was horrified by it. He was a classical physicist at heart. He believed in the continuity of nature. He wrote to a friend saying that his work was an act of despair. He felt he had to break the rules to make the math work. He didn't initially understand that he had discovered the bridge to a new way of seeing the world. He spent the next several years trying to understand what this Planck's constant actually was. He tried to fix the theory to make it consistent with the old ways. He couldn't. Then came Albert Einstein. In 1905, Einstein looked at what Planck had done, and he didn't see a mathematical trick. He saw reality. He took the idea of light quanta seriously. He used it to explain the photoelectric effect, how light hitting a metal surface knocks electrons loose. The classical theory said that if you shine enough light on a metal, eventually the energy would build up and the electron would be kicked out. It shouldn't matter what color the light was, just how bright it was. But experiments showed the opposite. It mattered which color you used. Red light, no matter how bright, did nothing. Blue light, even if it was very dim, and knocked electrons out instantly. Einstein said, "Look at Planck's idea. The light is coming in packets. One packet, one electron. But if the packet has enough energy, if the frequency is high enough, it kicks the electron. If it's too low, it's like a ball that doesn't have enough speed to climb the hill. It doesn't matter how many of those slow balls you throw in. They just bounce off. You need a fast one." That was the nail in the coffin for classical physics. It was the proof that the energy packets weren't just a convenient way to do math. They were the way light actually behaved. But let's go back to Planck for a moment. He was the one who opened the door. He was standing there holding the key, and he didn't even want to walk through. He kept trying to go back to the way things were. He was like a man who invented a new kind of engine, but kept insisting it was just a better kind of horse. The constant, Planck's constant, is tiny. It's roughly 6.6 times 10 to the power of negative 34 joule-second. That's a number with 33 zeros after the decimal point. That's why we don't notice it in our daily life. That's why the ramp looks like a ramp and why we don't feel the stairs. It's only when you get down to the level of atoms, to the scale of the very, very small, that the granular nature of the world starts to show. Think about the implications of this. If energy is quantized, then maybe position is too. Maybe time. That was the start of a wild ride. But we have to be careful. We shouldn't jump to conclusions. We have to stick to the evidence. Planck's discovery wasn't just about light. It was about the fact that our common sense, the sense we developed living in a world of medium-sized things, is completely useless when we look at the extreme. Our intuition, which tells us that everything is smooth and continuous, is a local phenomenon. It's valid here in our comfortable macroscopic home. But the universe is built on a different logic. A logic that deals in integers, in discrete steps, in counts. Consider the act of measurement. When you measure something, you're interacting with it. You are in some way touching it. If the energy is quantized, if there is a minimum unit of interaction, that Planck's constant, then you can't measure things with infinite precision. You're limited by the scale of the graininess. It's like trying to measure the length of a rug with a ruler that only has inch mark. You can't tell me the length is 5.2346 inches. You can only say it's between 5 and 6. This leads to some uncomfortable questions. If the world is granular, is it deterministic? If you know the state of a system, can you predict the future? Planck didn't want to go there. He wanted to keep the determinism of the old physics. He thought quantum theory would eventually be swallowed back up into the classical fold. He was wrong. But let's pause it. Why was the discovery so hard? Why did it take so long? Because we are trained to think in terms of fields and waves, water waves, sound waves. They are smooth. They are continuous. When you throw a stone in a pond, the ripple spreads out. It doesn't break into discrete packets. Light was supposed to be a wave, too. Maxwell's equations described light as an electromagnetic wave. It was a beautiful, successful theory. It predicted radio waves, X-rays, the whole spectrum. It worked perfectly. So when you see this particle behavior, when you see that light acts like it's made of little bullets, you feel a cognitive dissonance that you want to say, no, it must be a wave. And then you see the interference patterns, the double slit experiment, which we'll talk about another time, where light acts like a wave again. You end up with this duality, wave-particle duality. It's not that it's one or the other. It's that it's both or neither. It's a quantum object. And Planck was the first to touch this, to put his finger on the pulse of the quantum world without knowing what he was touching. He was looking at the heat, the thermal radiation. He was looking at how a hot object loses energy. It's a mundane problem. It's something you'd find in an engineering textbook. But he peeled back the surface and found the fundamental constant of the universe. That Planck's constant. It determines the scale of the quantum world. If Planck's constant were much larger, say if it were 1 joule second, the world would be a very strange place. You'd be able to see the stairs. You'd jump from one energy level to another. The atoms would be huge. Chemistry would be different. Life as we know it couldn't exist. We are alive and we can function because Planck's constant is so vanishingly small. We can pretend it's zero. We can pretend the world is continuous. And for most things, building houses, flying planes, cooking dinner, that pretense is just fine. But for understanding the stars, for understanding the sun, for understanding why the world doesn't fall apart, we need Planck's constant. We need the quantum. I remember thinking about this for a long time. How do you explain the transition? How do you go from a smooth curve, the Rayleigh-Jeans one, to the actual experimental curve? You have to acknowledge that the classical counting of states is just wrong. You have to use a different way of counting. It's a way that respects the graininess, and it's like counting apples in a basket. If you have an infinite supply, you don't care how you count them. But what if each apple costs a different amount and you only have a fixed budget? Then you can only buy so many. You can't buy an infinite number of apples, even if they're cheap. The constraint, the budget, limits the number of items you can pick. In the black body, the budget is the temperature. The cost of each state is the frequency. High frequency states are expensive. At low temperatures, you can't afford many of them. At high temperatures, you can afford more. That's why the color shifts. It's simple. It's intuitive once you see the analogy. But Planck didn't have the analogy. He had the math. He was pushing numbers around. He was a master of his craft, a man who understood the laws of thermodynamics so deeply that he could feel when they were straining. When he presented his work to the German Physical Society, he didn't realize he had started a revolution. He thought he had just solved the technical problem. He was like a man who found a loose thread on a sweater, pulled it, and suddenly the whole sweater started to unravel. He spent the rest of his life trying to knit it back together. And in a way, he was right to be skeptical. Quantum mechanics is weird. It defies common sense. It says that things don't have definite states until you measure them. It says that the observer is part of the system. It says that the vacuum isn't empty, but seething with fluctuations. It's a far cry from the clockwork universe of the 19th century. But nature is what it is. It doesn't care about our comfort. It doesn't care about our desire for continuity. It does what it does. And Planck, against his own inclinations, revealed the fundamental nature of that operation. Let's look at the mechanics of the act of despair again. He was trying to find a mathematical expression that fit the data. He used the Boltzmann entropy formula, which says entropy equals Boltzmann's constant, times the natural logarithm of the number of microstates. He applied it to the oscillators. He had to count the number of ways to distribute the energy, and to get the math to work, to get the result that matched the experimental curves, he had to assume the energy could be partitioned into little bundles. And this was the key. Before this, they thought about energy as a continuous distribution like a smooth line. If you had an energy E, you could divide it by any amount. But Planck found that if you force the energy into bundles of size energy equals Planck's constant times frequency, you get a different counting rule. This is the statistical origin of quantum mechanics. It's about counting. How many ways can you arrange these bundles? If you treat them as distinguishable versus indistinguishable, if you put them in boxes, if you do the combinatoric, that's where the physics is. It's not in the hardware of the oscillator. It's in the logic of the statistics. That's the deepest, most beautiful part of the discovery. The universe at its core is a counting problem. It's about how many ways you can put energy into space. And it turns out the universe is very restrictive about that. It has rules. It says you can't put energy just anywhere. You have to put it in specific configurations. And the cost of those configurations depends on the frequency. Why? Why does the energy depend on frequency? Why Planck's constant? Why not some other constant? We don't know. That's the honest answer. We observe that Planck's constant is a constant of nature. We measure it. It's the same everywhere. It's the same for an electron, for a photon, for a star. It's a fundamental scale. But we don't have a why beyond that. We don't have a deeper theory that derives Planck's constant from first principles. It is a given. It's a piece of the architecture of the universe that we just have to accept. Some people search for the deeper theory. They try to imagine the universe as a simulation or as a consequence of string theory or as a result of some high-dimensional geometry. And maybe they'll find something. Maybe they'll explain Planck's constant, though. But until they do, Planck's constant remains the defining number of the quantum age. Think of the impact on chemistry. Before this, we had the periodic table. We had atomic weights. But we didn't know why atoms behaved the way they did. Why do they form bonds? Why do they have specific shape? Why is carbon different from silicon? It's all because of these energy levels, dude. Because of the quantum. The electrons in an atom can only sit in specific energy levels defined by Planck's constant. They can't just sit anywhere. They have to fit into these slots. And when they fill up the slots, they have to go to the next level. That filling up, that exclusion principle, which we'll talk about later, that's what creates the chemistry. That's why you can have life. That's why you can have complex molecules. If energy were continuous, if you didn't have these discrete levels, the electrons would all spiral down into the nucleus. The atom would collapse. Matter as we know it would vanish, So Planck didn't just save the black-body radiation curve. He saved matter. He provided the foundation for the structure of the atom. And he did it by trying to solve a problem about heat. That's the beauty of physics. You look at one thing, a glowing stove, a piece of hot iron, and you end up describing the structure of the entire universe. You peel back the layers, and the simple, everyday object turns out to be a window into the most profound mysteries. I remember when I first really grasped this, when I understood that the catastrophe wasn't just a math error, but a signal, a flag waving from the quantum world saying, hey, look here, something weird is going on. I felt a shiver. It's a kind of excitement you can't describe to someone who hasn't felt it. It's the thrill of seeing behind the curtain. It's not magic. It's not a miracle. It's just how things are. And the only thing separating us from the reality of the quantum world is our own limited perspective, our own insistence that the world should be smooth because that's what we see with our eyes. But our eyes are just senses. They aren't the truth. Our eyes evolved to see the world of medium-sized things at medium speeds, at medium temperatures. They didn't evolve to see the quantum world. So we have to use tools. We have to use math. We have to use logic. And we have to be willing to follow where the evidence leads, even if it's somewhere we don't want to go. Planck didn't want to go to the quantum world. He was dragged there, kicking and screaming by the data. And that's the lesson. You follow the data. You don't follow your prejudices. You don't follow what you know to be true. You follow the numbers, the experiments, the reality. And if the reality says the energy is quantized, then it's quantized. No matter how much it makes your head hurt, no matter how much you wish it were different. Now let's consider the way we teach this. We often talk about the discovery of the quantum as a eureka moment, like someone jumped out of a bathtub and shouted, "Energy is discrete." It wasn't like that. It was a long, slow, grinding process, a struggle. Planck went through months of doubt, of trying to patch the holes, of trying to force the square peg of reality into the round hole of classical theory. He wasn't trying to be a revolutionary. He was trying to be a good physicist. He was trying to reconcile his results with the accepted wisdom. That's what a good scientist does. You respect the past, you respect what came before, but you don't let it blind you. This is something we forget. We see the history books and we see the names. Planck, Einstein, Bohr, Heisenberg. We think they were gods. We think they knew everything. They didn't. They were just people standing in a room and looking at a board, trying to make sense of a mess. They made mistakes. They had bad ideas and they got things wrong. And the history we tell is the filtered version, the cleaned up story where everything fits together nicely. The real story is messy. It's full of blind alleys, false starts, and confusion. The discovery of the Planck constant is a perfect example of that. It's a human story, a story about a man who opened a door he didn't realize existed, and then spent the rest of his life wondering if he should have left it shut. But it's also a story about the power of honesty. Planck could have fudged the data. He could have ignored the bits that didn't fit and went through. He could have claimed his formula was just an approximation and left it at that. But he didn't. He published the formula. He put it out there. He exposed it to the world. And in doing so, he allowed others, Einstein, Bohr, and the rest, to pick up the baton and run with it. That's the scientific community in action. It's not about the individual hero. It's about the collective enterprise. It's about putting your best effort, your best insight, your best guess on the table and letting the world test it. And if it survives, if it's true, then it becomes part of the shared knowledge of humanity. Think about the implications of the constant. It sets the scale of action. In physics, action has a specific meaning, energy times the time. It's a dimension. It's a way of measuring change. The Planck constant has the dimensions of action. It means that there is a minimum unit of action. You can't have an action less than Planck's constant. This is the basis of the uncertainty principle. Because you have a minimum unit of action, you cannot simultaneously know the position and the momentum of a particle with infinite precision. The product of the uncertainties is on the order of Planck's constant. If you know the position exactly, the momentum becomes totally uncertain. If you know the momentum exactly, the position becomes totally uncertain. This is a direct consequence of the graininess. If the universe were continuous, you could measure everything with infinite precision. But because it's grainy, because there is this fundamental constant, Planck's constant, there is a limit to what you can know. There is a fundamental fuzziness to realities. And again, this is not a limitation of our measuring instrument. It's not that our microscopes aren't good enough. It's a property of the universe itself. The universe refuses to be measured with infinite precision. It's like it has a resolution limit. This is a profound, deep, unsettling fact. And it all stems from that simple problem of the glowing stove. It all stems from trying to figure out why the stove doesn't spit out infinite energy when you turn it on. I sometimes wonder what would have happened if Kirchhoff, the guy who first defined the blackbody problem, had solved it. He was a brilliant man, but he didn't have these statistical tools that Boltzmann had developed. He was missing the key. He saw the problem, he defined it, he set the stage, but he couldn't solve it. It required a combination of ingredients, the experimental data from the labs, the statistical mechanics from Boltzmann, and the persistence of Planck. It was a unique moment in history. If one of those pieces had been missing, the discovery might have been delayed for years, maybe decades. We like to think that progress is inevitable, that if we don't discover something today, someone else will tomorrow. And in the long run, that's probably true. But in the short run, the individuals matter. Their insight, their struggles, their choices matter. Planck had a choice. He could have been a normal physicist. He could have worked on safe, established problems. He could have had a quiet, comfortable career. Instead, he took on the hard problem. He took on the problem that everyone else was avoiding or failing at. He took the risk. And that's what separates the great from the good. It's not about being smarter than everyone else. It's about being willing to look at the hard problems, to face the confusion, to stand in the dark and wait for a spark. And when that spark comes, when you finally see the connection, when the pieces click into place, it's not a feeling of triumph, it's a feeling of relief. Oh, that's it. That's how it works. That's it. And then almost immediately you start to worry. Is it right? Did I miss something? Is there a trap? That's what Planck felt. And that's what Einstein felt. And that's what anyone who has ever tried to understand nature feels. It's a mix of excitement and anxiety. It's the price of admission. So when you think about the Planck constant, don't just think about 6.6 times 10 to the negative 34. That's just a number. Think about the struggle. Think about the glowing stove. Think about the transition from the ramp to the stairs. Think about the shift from a world of smooth, continuous waves to a world of quantized, discrete packets at this alpha. Think about the fact that we are living in a quantum world, and even if we can't see it, think about the fact that the computer you're using, the light you're reading by, the air you're breathing, it's all governed by these quantum rules. It's all a manifestation of the quantum nature of reality. And it all started because a guy in Berlin wanted to know why his stove changed color. It's almost funny, isn't it? The biggest discoveries often start with the smallest, most ordinary things, the things we take for granted, the things we ignore. But if you look at them closely, if you really pay attention, you find the universe staring back at you. We are so used to the idea that physics is about exotic things, black holes, the Big Bang, dark matter. And yes, those are fascinating. But the real physics, the stuff that builds the world, is in the everyday. It's in the heat of your coffee. It's in the light of the lamp. It's in the vibration of the atoms in your chair. And if you can understand those, if you can trace them down to the quantum level, you understand everything. That's the dream of physics anyway. To find the rules, the simple underlying rules that govern all of it, from the smallest particle to the largest galaxy. We aren't there yet. We still have pieces that don't fit. We have gravity, which doesn't play well with quantum mechanics. We have the dark matter, which we can't see. We have questions that we don't even know how to ask yet. But we have the constant. We have Planck's constant. It's our anchor. It's the signpost that tells us where we are in the universe. It's the one thing we can hold on to, the one thing we know for sure. It's the quantum, and that's enough. But now it's enough. Let's think for a second about what it means to be right. Planck was right, but he didn't know why he was right. He had the correct equation, but the wrong interpretation. Does that count as being right? In physics, it does. If your equation predicts the outcome of the experiment, that you're on the right track. The interpretation, the story you tell about what the math means, that comes later. Usually the math is ahead of the physics. The math is a map that takes us into new territory. And then the physics catches up, helping us understand where we've arrived. And that's what happened with Planck. The math said there is a quantum. The physics said that's impossible. and the math won. The physics had to change. That's a pattern you see again and again. The math tells us things we don't want to believe. It tells us the world is weirder, smaller, and more connected than we ever imagined. And we fight it. We try to interpret it in terms of what we know, but eventually we have to let go. We have to accept the new reality. It's not just in physics, it's in everything. When you learn a new skill, when you encounter a new way of thinking, when you face a challenge that doesn't fit your past experience, you go through this same process. You try to force it into your old mental models, and when that fails, you have to create a new model. You have to change your understanding of the world. Planck had to change his world. He had to give up his belief in the classical, continuous universe, and it hurt. He resisted it. He fought it, but he did it. Can you do that? Can you change your mind when the evidence is staring you in the face? Can you let go of your most cherished beliefs when they no longer fit the facts? That's the hardest thing in the world. It's harder than solving the black body problem. It's harder than discovering a new constant. But that's what it means to be a thinker, to be a learner, to be human. So the next time you look at a light bulb or a fire or the sun, don't just see the light. See the quantum. See the graininess. See Planck's constant. And remember the man who found it. Not because he was a genius who could see the future, but because he was a persistent, honest, and slightly stubborn man who just wanted to understand why his stove was glowing red. That's the beauty of it. You don't have to be a genius. You just have to be curious. You just have to be willing to look. Now, I've been talking for a while, and I want you to go home and think about this. Think about the stove. Think about the constant. Think about the stairs versus the ramp. And maybe, just maybe, you'll start to see the quantum world in everything you do. And if you get confused, and you will, because this is confusing stuff, but don't worry, that's part of the process. If you're not confused, you're not paying attention. The confusion is the best part. It's the sign that you're learning something new. It's the sign that you're pushing against the boundaries of your own understanding. So embrace the confusion. Lean into it and see where it takes you. Because that's how the real work happened. And that's how we move forward. One step, one experiment, one question at a time. And who knows, maybe you'll be the one to solve the next big mystery. Maybe you'll be the one to find the next constant. But for today, this is enough. And we've covered a lot. We've gone from the stove to the atom. We've gone from the classical to the quantum. We've seen the struggle of a man who changed the world even if he didn't want to. And that, to me, is the best kind of story. I want you to really visualize the cavity. Imagine a hollow box. The walls are perfect reflectors, or they emit and absorb radiation, a black body. You heat the box. The radiation inside starts to bounce around. It hits the walls. It's absorbed and re-emitted. It's a thermal equilibrium. The radiation inside that box is what we're talking about, the black body radiation. And it's the same spectrum, whether the box is made of iron or gold or silver. It's universal. It depends only on the temperature. That's the beauty of it. It's independent of the material. That's why Kirchhoff was so interested in it. It's a fundamental feature of the universe. So imagine you make a tiny hole in the box, a little bit of that radiation leaks out. That's the light you see. That's the light that Planck was studying. And his goal was to describe the intensity of that light as a function of its frequency for a given temperature. He had the experimental data. He had the curves. He saw that at high frequencies, the intensity dropped off exponentially. That was Wien's part. And at low frequencies, it was proportional to the square of the frequency. That was the Rayleigh-Jeans part. His interpolation was a simple mathematical trick. He took a formula that looked like the intensity is proportional to the frequency cubed divided by the quantity exponential of Planck's constant times frequency divided by Boltzmann's constant times temperature minus 1. It's a beautiful formula. It's simple, it's elegant, and it covers everything. It handles the high frequencies and the low frequencies. But why the exponential? Why the minus 1 in the denominator? That -1 is the footprint of the quantum. If the -1 weren't there, you'd get the classical Rayleigh-Jeans result. That -1 is what kills the infinite energy. It's the difference between a catastrophe and a stable universe. I used to stare at that equation on the board for hours, just looking at the symbols: Planck's constant, frequency, Boltzmann's constant, temperature. It's just letters, but they represent the fundamental structure of the physical world. They represent the connection between the heat of an object and the energy of its light. It's amazing how much is packed into that one little expression. If you ever find yourself wondering if physics is too hard or if you're not smart enough to understand it, remember this: Planck himself didn't understand the significance of his own formula at first. He had to be dragged into it. He had to be convinced by the evidence. You don't have to have an intuition for the quantum world. Nobody does. Even the experts, even the ones who developed the theory, Einstein, Bohr, Heisenberg, Schrödinger, they all struggled with it. They all had doubts. They all had to change their way of thinking. So if you're confused, join the club. You're in good company. The thing is to not stop. The thing is to keep asking questions. Why? How does that work? What if I tried this? That's the secret. That's the only secret there is. You don't need fancy equipment. You don't need a supercomputer. You just need a mind that is willing to be wrong. A mind that is willing to accept that the world might not be what it seems. And that is a very rare thing. It's the rarest thing in the world. So practice it. Practice being wrong. Practice letting go of your assumptions. Practice the art of not knowing. Because in that state, in that space of uncertainty, that's where the discovery happens. That's where the light comes in. It's just like the box on the critical knot. If the box is sealed, if it's full of your own ideas, nothing new can get in. But if you make a little hole, if you open it up, if you let the world, the real world, the evidence, the facts stream in, and then you see the radiation, then you see the truth. It's not always pretty. Sometimes it's uncomfortable. Sometimes it's strange. Sometimes it's the opposite of what you expected. But it's real. And that's what matters. So keep the hole open. Keep looking. Keep asking. And don't worry about the answers. The answers are just the start of the next question. The Planck constant, H, it's not just a number. It's a boundary. No? It's the line between the world of the human and the world of the quantum. And we're standing on that line, looking both ways. It's a good place to be. It's a place of wonder. And it's a place that is waiting for you. So go explore. Go think. Go wonder. Because that's what we do. We're scientists. We're observers. We're parts of the universe trying to understand itself. And that's the most exciting adventure there is. I want to share something with you about the way we talk about science. We often use words like discovery or breakthrough or revolution. We make it sound like a war or a battle or a sudden flash of light. But the reality, the day-to-day work is much more boring and much more difficult. It's about being wrong, failing, starting over, and repeating the process. Planck's work wasn't a sudden explosion of insight, and it was a tedious, agonizing slog. It was about trying to get the math to fit the curve. It was about adjusting one parameter, seeing it fail, adjusting another, seeing it fail again. It was a process of trial and error, and that is the reality of science. It's a process of elimination. You rule out the things that don't work, and what you're left with, no matter how strange, is the truth. If you understand that, if you accept that, and you're already halfway there, you're already ahead of most people because you're not looking for the magic answer. You're looking for the hard, difficult, persistent truth. And that's what leads to the breakthrough. That's what leads to the Nobel Prizes, but more importantly, that's what leads to understanding. and understanding is the only thing that really matters. So don't be afraid to fail. Don't be afraid to be wrong. Don't be afraid to struggle with the math, because the struggle is where the learning happens. The struggle is the work. And if you can enjoy the struggle, if you can find the joy in the confusion, then you'll never stop learning. You'll never stop growing. You'll never stop discovering. And that's the best life you can possibly have. Now, I think I've said enough for today. So we've covered a lot of ground, and I want you to go home, grab a piece of paper, and try to rederive the black-body curve yourself. Or better yet, just think about the problem. Imagine the box, imagine the radiation, imagine the stairs. See if you can get to the same place Planck got to, not by following his path, but by following your own, by thinking it through for yourself. That's how you learn physics. Not by memorizing equations, but by understanding the problem, by living with it, by struggling with it, and by finding your own way to the answer. It's not easy. It's probably one of the hardest things you'll ever do, but it's worth it. Because when you finally see it, when it finally clicks, it's a feeling like no other. It's the feeling of understanding the world. And that is a feeling you should cherish. So go out there and think. Go out there and wonder. And remember the constant. Remember Planck's constant. Remember the stove. And above all, remember to keep your mind open. And thank you. Today's lecture is about quantum entanglement and why it terrifies physicists. Let's start with a problem that bothered Einstein until the day he died. Not because he was slow, he was one of the sharpest minds we ever had, but because he couldn't stomach the idea that nature might be playing dice with the fundamental rules of how things work. He wanted a world that was local, a world where things happen here because something pushed them here, not because something happened on the other side of the moon. I remember sitting in my office at Caltech staring at a chalkboard covered in scribbles, trying to explain this to a student who kept asking me why the math worked the way it did. I didn't have an answer then. I don't have a perfect answer now, and that is exactly what makes this subject so peculiar. Think about a pair of gloves. You have two gloves, one left, one right. You put them in two separate boxes. You take one box to New York and send the other to Timbuktu. Now, the person in Timbuktu opens their box. They see a left-hand glove. Instantly, they know that the box in New York contains the right-hand glove. There is no mystery here. You don't call up the physics department and scream about a breakthrough. You just have a pair of gloves. The information about which glove which was already fixed the moment you packed the boxes. Physics used to be like that. We assumed that if you had two particles, they had definite states before you measured. If you measured the spin of one and it was up, the other had to be down. The state was determined before you even looked. That is what we call local realism. It is the bedrock of how we experience the world. You touch a hot stove, your hand burns. The heat transfers because the molecules in your skin hit the molecules in the stove. Everything touches everything else to make things happen. But then the quantum mechanics showed up, and it turned out that the world doesn't behave like a pair of gloves. Imagine you have two electrons. You create them in such a way that their total spin is zero. They are entangled. Now you separate them. You send one to the far side of the universe, and you keep one right here in the room. According to the old school way of thinking, each electron has its own properties, its own spin, just waiting to be measured. But quantum mechanics says no. Before you measure it, that electron doesn't have a spin. It is in a superposition. It is, in a sense, both up and down at the same time. It is a blur of probability. The moment you measure the one in your room, the probability wave collapses. You see up. And at that exact, precise, instantaneous moment, the other electron, the one on the other side of the universe, becomes down. It happens faster than the speed of light. It happens without a signal passing between them. If you try to tell me there is a wire connecting them or a ghost signal flying through space, the math says you are wrong. The correlation is perfect. And it is this spooky action at a distance, as Einstein called it, that makes the whole thing feel like a violation of the rules. When I was working at Los Alamos, we spent a lot of time thinking about how information moved. We had these massive problems to solve, trying to figure out if an implosion device would actually work. But we had to trust that things were local. If you change a parameter here, the result changes there because of a sequence of events. If the world were governed by entanglement in our daily lives, building a bomb would be impossible because you could never guarantee the state of the material. You would just be hoping the universe decided to cooperate. Einstein hated this. He argued that quantum mechanics must be incomplete. He thought there were hidden variables. He believed there was a secret instructions list inside the particles, something we weren't seeing, which determined the outcome beforehand. Like the gloves, if we could only see the hidden variables, the spookiness would disappear. For a long time, we couldn't test this. It was just philosophy. People would argue in the halls, drink coffee, and draw diagrams, but nobody could build an experiment to settle it. Then a fellow named John Bell came along. Bell did something brilliant. He didn't just guess. He proved that there is a limit to how correlated two things can be if they are governed by local hidden variables. He created an inequality, a mathematical line in the sand. If the world followed the gloves theory, the Einstein theory, the correlation would stay below a certain number. If the world followed the quantum theory, the correlation would cross that line. And it was one of the most important moments in the history of physics. We finally had a way to ask nature the question directly. I recall when the experiments finally started to get precise enough to test this. You have to set up these polarizers. You measure the spin of particle A along one axis and particle B along a different axis. You run the number. You check if the correlations violate the inequality. And every single time we do it, nature crosses the line. It doesn't care about our intuition. It doesn't care that Einstein thought it was wrong. It just does what it does. Now, why does this terrify people? Why does it bother us so much? It's because of what it implies about space. We think of space as a stage where things are separated by distance. If I am here and you are there, I cannot influence you instantly. I have to throw a ball. The ball has to travel. That takes time. Space separates us, and that separation prevents us from being one thing. Entanglement suggests that at a very fundamental level, distance might be an illusion. If two particles can be correlated in a way that ignores the distance between them, maybe they aren't actually separated. Maybe the idea of here and there is just a way we carve up the world, but the world itself doesn't recognize those boundaries. I remember thinking about this while walking through the tunnels in Ithaca. It's an uncomfortable feeling. You want to believe in an objective reality where things exist independently of whether you are looking at them. You want a world where an electron is just a little billiard ball with a specific direction of spin. But the math and the experiments, they don't let you keep that comfort. The math says that the particles share a single wave function. They are part of one system. You can't talk about particle A without talking about particle B. They are not two things, they are one thing, just stretched across the universe. So is there a secret message passing between them? Can we use this to talk to Mars instantly? Here's where the confusion usually hits. People get excited. They think, aha, we can send messages faster than light. But you can't. If I measure my electron and I get up it, I know the other one is down. But I cannot force my electron to be up. It's random. I can't control the outcome. And since I can't control the outcome, I can't send a signal. The person on the other end sees a random sequence of up and down. They don't know if I measured mine or not, and they only realize the correlation when they bring their data back to my lab and we compare the lists. So information is not traveling faster than light. Causality is preserved. The universe is still safe in a sense, but the connection is still there. This creates a split. We have the shut up and calculate crowd. Like they say, look, the math works. The predictions are accurate. Just use the equations and don't worry about the philosophy. And then you have the ones who keep digging, the ones who get ulcers over it. I suppose I've always been in the second camp. I don't want to just calculate it. I want to feel the physical mechanism. I want to see the gears turn out. And in entanglement, the gears are hidden. Or maybe the gears aren't there at all. Let's try to visualize it differently. Imagine two dancers. They are on opposite sides of a stage hidden behind curtains. They have never rehearsed. They don't have a plan. But the moment the curtains rise, they start dancing in perfect synchronization. If one spins left, the other spins right every single time. You would assume they were whispering to each other, or they had a secret agreement, or they were practicing for weeks. But what if they weren't? What if they were just connected? That is the quantum state. It makes me think of the early days of quantum mechanics, back when we were still figuring out the basics. Bohr, Heisenberg, Schrödinger, they were all trying to fit this into a box. They were trying to make it match the world we see. But the world we see is a macroscopic limit. It's a fuzzy, averaged out version of the truth. When you zoom in, when you look at the electron, the billiard ball is gone and the certainty is gone. Is it possible that we are missing a layer? Is it possible that there is a theory deeper than quantum mechanics? It's something that explains why this entanglement happens? Maybe. Many people have tried to find it. They've written papers, built models, proposed all sorts of weird stuff, but so far nothing has replaced the quantum theory. It remains one of the most accurate descriptions of reality we have ever produced. The discomfort comes from the feeling that we are missing something fundamental. We feel like we are looking at the shadow of a much larger, more complex shape, and we are trying to guess the shape just by looking at the shadow on the wall. Think about the implications for gravity as there are all. We don't have a good theory of quantum gravity. General relativity describes a smooth, curved space-time. Quantum mechanics describes a choppy, probabilistic universe. They don't get along. They fight. And entanglement sits right at the center of that fight. Some of the brightest people today are trying to figure out if space-time itself is built out of entanglement. Imagine that. The distance between me and the back wall, the fabric of the cosmos, the shape of the universe, it might all be a byproduct of these quantum links. It sounds like science fiction, but that's how physics works. You start with something impossible, you test it until you're blue in the face, and then you accept that reality is just stranger than you thought. Let's go back to the experiment for a second. Suppose you measure the polarization of photons. If you have a photon source, it emits two photons in opposite direction. You put a filter, a polarizer in the path of each photon. You can rotate the angle of the polarizer. If you align both polarizers at the same angle, you get perfect correlation. But if one lets light through, the other does too. If you rotate one, the correlation changes according to a specific law. The cosine squared of the angle different. And this is the key. The way the correlation changes is the fingerprint of quantum mechanics. The hidden variable theories, the local realist theories, they predict a different curve, a linear curve or something else. They don't predict that specific cosine squared curve. When we measure it, the curve follows the quantum prediction. It's exact. So we know the particles are linked in a way that classical objects cannot be. We know that the state of one is not defined until the measurement happens. And we know that this behavior is robust. We can do this with photons, with electrons, with ions. even with large molecules. The question remains, why? Why does nature do this? I used to go down to the local diner just to get away from the office. I'd sit there with a coffee and a notebook. I'd watch the cars go by, the people walking, the rain hitting the window. It all feels so continuous, so solid. You have a cup of coffee. It stays a cup of coffee, it doesn't become a cloud of probability. It doesn't get entangled with the coffee in the next town over. The macro world is different from the quantum world because of decoherence. When a quantum system interacts with the environment, bumping into air molecules, light, dust, the entanglement leaks out. It gets lost. It gets smeared across the environment. So for big things like coffee cups and cars, the quantum effects are washed out. They are effectively hidden. But that doesn't mean they aren't there. It just means we are blinded by the sheer noise of the world. If we could isolate a system perfectly, if we could keep it cold and quiet, the entanglement would be visible. We have technology now that lets us do that. We have traps for atoms. We have superconducting circuits. We are creating these entangled states on purpose. We are playing with them. We are building computers that use this spooky behavior to solve problems that would take a normal computer the age of the universe to crack. So we are moving from this is a philosophical nightmare to this is a tool. We are engineering the spookiness, but even as an engineer, even as someone who builds the circuits, the feeling of unease persists because we are manipulating something we don't fully understand. We are like children playing with a radio. We know which knob turns the volume up and we know which switch changes the station, but we don't know how the radio waves travel through the air. We don't know what the field is. That is the humble truth. We have the rules, the Schrödinger equation, the density matrices, the operators, but we don't have the intuition. We don't have the why. I remember once I was trying to explain to a high school class how the double slit experiment works. It doesn't work. You fire electrons at two slits and you get an interference pattern. It's like waves in water. If you look at which slits the electron goes through, the pattern disappears. It becomes two bands. The student asked, but where is the electron when you aren't looking? And I told him, you shouldn't ask that. I was half joking, but I was also serious. The question assumes the electron is somewhere. It assumes that somewhere is a meaningful concept for an electron. But in the quantum view, somewhere is a feature that emerges from the measurement. Before the measurement, the electron is a range of possibilities, a wave of potential, and entanglement is just the double slit experiment turned up a notch. It's the same refusal of nature to be pinned down. It's the same insistence that the system is global, not local. Now, are there limits to this? Could the whole universe be entangled? Some physicists argue that the entire universe started as a single point, a singularity. If that's true, then everything in the universe started in an entangled state. Maybe in some deep, profound sense, everything is still entangled. Maybe the reason gravity acts the way it does is because the particles are still to some degree maintaining that initial ancient connection. That is a bold thought. It's speculative, but it's the kind of thought you have when you stare at these equations long enough. Let's look at the terrifies part of the title. Why should physicists be afraid? Fear is the wrong word. It's more like an itch you can't scratch. It's the feeling of being wrong about something fundamental. We like to think that we have made progress. We went from Aristotle to Newton, from Newton to Maxwell, from Maxwell to Einstein. Each step was a refinement. Each step gave us more control, more power. But quantum mechanics feels like a discontinuity. It feels like we walked into a dark room and found that the floor was made of jello. You can stand on it for a moment, you can walk across it if you're careful, but you can't trust it to be a solid floor. And that uncertainty, that instability, it makes us uncomfortable. We want the floor to be rock. We want the universe to be understandable in terms of simple, local, solid objects. But the universe doesn't have to be what we want. I've had students come to me, brilliant kids, really sharp, and they ask, can we just interpret it differently? Can we use the many worlds interpretation? Can we use pilot waves? Can we use collapse models? And I tell them, sure, pick your poison. Because all of these interpretations lead to the same math, and they all predict the same experimental results. The math is the only thing we have that works. The interpretation, they are just stories we tell ourselves to help us sleep at night. They are the pacifiers we use to deal with the fact that the math is counterintuitive. Many worlds, it says every time a measurement happens, the universe splits. Every possible outcome happens in a different non-interacting branch of reality. It saves locality, but at the cost of an infinite number of universes. Is that a price you want to pay? Pilot waves, it says there are particles that really do have definite positions, and they are guided by a hidden wave that exists in the background. It saves realism, but at the cost of non-locality, the wave has to know about everything, everywhere, instantly. Collapse models, they say there is a physical process that causes the wave function to snap into a single state randomly. It solves the measurement problem, but it requires us to modify the laws of physics to add a term to the equation that we haven't seen yet. Each one of these takes something we hold dear and breaks it. Each one requires a sacrifice. And that is why entanglement is terrifying, because it forces us to choose what we are willing to give up. Are you willing to give up locality? Are you willing to give up realism? Are you willing to give up the idea that the universe is simple? I think the reason I spent so much time on this, the reason I played with the path integrals, the diagrams, the sum over histories, was because I wanted to find a way to make it all fit together without the sacrifice. I wanted a way to calculate, to predict, to understand, without having to invent 100 universes or hidden ghost waves. I didn't find it. I don't think anyone had. Maybe the point isn't to fix it. Maybe the point is to live with it, to accept that nature is just like this. Think about the way you learn to swim. You don't learn by reading a book on fluid dynamics. You jump in, you flail, you get water up your nose, you panic, you try to fight the water, you try to grab onto the water to hold yourself up, and that doesn't work. The water doesn't care. Then eventually you stop fighting. You relax and you let the water support you. You realize the water has its own way of moving and you have to move with it, not against it. Physics is like that. We spend years trying to force nature to be what we wanted it to be. We wanted it to be logical. We wanted it to be intuitive. We wanted it to be local. And then one day, you stop. You realize the universe doesn't owe you an explanation that makes sense to your brain, which evolved to hunt for food and avoid predators on the African savanna. Why should our brains be capable of understanding the fundamental structure of reality? Dude, that's a miracle if you think about it. So when you see a paper about entanglement, or you hear someone talking about quantum teleportation, don't get hung up on the teleportation or the spookiness. Those are just words. They're just metaphors. The reality is the correlation. The reality is the math. The reality is that the universe is linked in ways that defy our everyday logic. And that is a beautiful thing. It means the world is richer, deeper, and more surprising than we ever imagined. Let's dig a bit deeper into the history. When Einstein, Podolsky, and Rosen, the EPR paper, came out, they were really trying to prove that quantum mechanics was incomplete. They thought they had caught the theory in a lie. They said, look, if we can predict the state of particle B by measuring particle A, then particle B must have a defined state all along. And if quantum mechanics says it doesn't, then quantum mechanics is wrong. It was a logical argument. If A is true and B is true, then C must follow, and it was perfectly sound. The only problem was the premise. The premise that objects have defined states turned out to be false. It's like asking, if I have a fair coin, what is the outcome of the flip we solve? The answer is the coin doesn't have an outcome until it lands. But they were arguing about the nature of the coin. And they were saying, no, the coin must have a side face up, even while it's in the air. You just haven't looked at it yet. And quantum mechanics was saying, no, the coin is a blur of heads and tails while it spins. It is both. It is neither. It is a probability distribution. Einstein couldn't accept that. He wanted the coin to be heads or tail, but he wanted the world to be definite. Now imagine if you could flip two coins at the same time in different rooms and they always landed on the same side, even though each coin was a fair flip. Even though you couldn't control it, that would be weird, right? And you would say, hey, there's a mechanism linking these coins. But in quantum mechanics, it's not even that. It's like the coins are flipped, and they are both heads and tails simultaneously, and only when you stop them do they settle. And the link ensures that if one settles on heads, the other settles on heads. It's not just that they are correlated, it's that they are undefined until the correlation is tested. This is the hardest part to wrap your head around. It's the part that makes students stay up all night. If the particle doesn't have a spin, how does it know which way to spin when the other one is measured? It doesn't know. That's the wrong word. Knowing implies a process, a calculation. The system just is. It satisfies the constraints of the wave function. It's a global solution to a local problem. I used to use the analogy of a drum. If you hit a drum, the sound isn't localized to just one point on the skin. The whole drum head vibrates. Every part of the drum moves in harmony with every other part. You can't say that this part of the drum is vibrating because I hit it, and that part is vibrating because, well, I don't know. The vibration is a property of the whole drum. Entanglement is like that. The particles are the drum. The measurement is the tap. The correlation is the sound. This also explains why we can't send signal. You can't play a melody on the drum by only touching one point and expecting that to be the only thing that happened. If you tap the drum, the whole surface responds. If you tap it somewhere else, you get a different sound. But if you're trying to send a message to someone on the other side of the drum, you can't control the specific vibration pattern in a way that encodes information, because the drum is a physical system that follows its own laws. It's a bit of a stretch, this analogy, but it's better than the hidden variable stuff. I think the reason we keep coming back to entanglement is that it hints at something we haven't solved yet. It's a loose thread. We pull on it and the whole sweater starts to unravel. Gravity, thermodynamics, information theory. It all seems to point back to this weird entangled structure. There is a concept called black hole information paradox. You throw a book into a black hole. The information about the words in the book, the atoms, the state, the entanglement, what happens to it? Does it vanish? If it vanishes, that violates the laws of quantum mechanics, which say information must be preserved. And if it stays, where is it? Maybe it's encoded on the surface of the black hole. Maybe it's entangled with the Hawking radiation that comes out. This is the frontier. This is where the best minds in the world are currently beating their heads against the wall. And it's all at the bottom about entanglement. I remember meeting some of these people at conferences, of course. They have this intensity, this wild look in their eyes. They aren't interested in the easy stuff anymore. They want to know what the universe is made of. And they're all betting on entanglement. Is it possible that space itself is woven out of entanglement? That the reason we have space and time is because we have these quantum correlations? That is a deep thought. It implies that before there was space, there was entanglement. Before there was a where, there was a relationship. Think about that. A relationship without a place. It sounds like poetry, but the math is starting to look that way. The geometry of space-time seems to be related to the entropy of entanglement. The more entangled things are, the more space you have. If this turns out to be true, then Einstein was wrong about the gloves, but he was right that gravity is geometry. It's just that the geometry isn't the fundamental thing. The geometry is the emergent thing. The geometry is the shadow. The entanglement is the light. When I was a kid, I used to fix radios. I loved taking them apart, seeing how the wires connected and how the resistors and capacitors interacted to create the sound. I wanted to understand the machine. Entanglement is like the ultimate radio. It's a machine that works in ways that aren't obvious from the wiring diagram. You look at the wires and you say, this shouldn't work. And then you turn it on and the music plays. And you realize the wiring diagram is wrong. The wires aren't just wires. They are paths for a field. They are part of a larger structure. I think that is the lesson of entanglement. Our wiring diagrams that are classical physics, our common sense, and our intuition, like a just approximation, they are useful for building bridges and radios and airplanes. But when you get to the level of the electron, the wiring diagram breaks. And you shouldn't be afraid of that. You should be excited. Because if the world was simple, and if the world were just a bigger version of the things we see every day, it would be boring. The fact that it's weird, that it's spooky, that it defies our common sense, that is what makes it interesting. That is why we do physics, not to confirm what we already know, but to find out what we don't know, to push the boundaries, to see where the map ends, and then to walk off the edge into the unknown. I sometimes wonder what Einstein would think if he were alive today. He died before the experimental proof of Bell's inequality. He died still fighting the quantum theory. I like to imagine him reading the results of the aspect experiment. I think he would have been frustrated, sure. He would have hated it. He would have tried to find a loophole. He would have spent weeks, months, years trying to prove the experiment wrong. And then, when he realized he couldn't, I think he would have been the first one to say, well, then, we have a lot more work to do. He was a scientist, after all. He followed the evidence, even when he didn't like the result. That is the integrity you need. You have to be willing to be wrong. You have to be willing to look at the data and say, okay, my intuition was wrong. The universe is not the way I thought it was. Most people can't do that. They cling to their ideas. They protect their theories like they are guarding a treasure. But in science, the treasure is the truth. And the truth doesn't care about your theories. The truth just is. So don't worry about understanding it perfectly. Nobody does. Feynman, Einstein, Bohr, we were all just trying to catch up to the reality of the situation. We were all just students in a way. The mystery is the point. The question is the point. And if you ever find yourself thinking you understand quantum mechanics, you're probably wrong. You're probably just looking at the math and mistaking it for the reality. You have to keep the itch. You have to keep the question alive. Because the moment you say, I understand, you stop learning. And that is the death of science. We have this tendency as humans to try and label things, to put them in categories, to say this is a wave and this is a particle. But nature doesn't have labels. Nature doesn't have categories. Nature just has behavior. Entanglement is a behavior. It's a way that matter acts. It's a way that the universe maintains consistency across distances. We don't have to call it non-locality or spooky action. We can just call it the way things are. I think that's the most Feynman-like advice I can give. Don't get hung up on the words. Don't get hung up on the labels, and look at the phenomenon. Look at the data. Look at the experiment. And if it contradicts your common sense, don't throw out the experiment. Throw out your common sense. Your common sense was built for throwing rocks and dodging lions. It wasn't built for understanding the fundamental structure of space and time. It's a miracle it works at all. There is a moment in the lab, right before you take the data, when you have everything set up, the equipment is humming, the lasers are aligned, the detectors are ready. You are about to ask nature a question, and you don't know the answer. That is the best moment. That is the moment of pure possibility. And entanglement gives us so many questions. We can test it with different particles. We can test it with different distances. We can test it with different conditions. We can test it until we understand the limits. And then maybe we will see the next layer. Maybe we will see what lies beneath the entanglement. I suspect that the answer will be something simple. It's something so simple that we will look back and laugh at how confused we were. We will say, of course, and it was obvious. Why didn't we see it sooner? But until then, we have the mystery and we have the math. And that is enough. Let me talk about the locality assumption again. It's really the core of the problem. We assume that for an event at point A to affect an event at point B, there must be a chain of events connecting them. The speed of light is the speed limit of these causal chains. Nothing can go faster. So when we see an instantaneous correlation, we feel like the speed limit has been violated. We feel like the law has been broken. But the speed limit applies to the transmission of information. It applies to sending a message. If I try to send you a bit of data, I have to obey the limit. But entanglement isn't about sending a message. It's about the state of a system. The system is already there, and so it's already prepared. It's like having a deck of cards. You shuffle the deck, you split it into two halves. You give one half to me and one to you. You fly to New York. I stay in London. We both open our halves. We realize that the cards are arranged in a specific way. The order is correlated very clear. Did the cards communicate at the speed of light to arrange themselves? No. The order was established when we shuffled the deck. The difference in quantum mechanics is that the shuffling happens in a way that doesn't define the cards until we look. It's a shuffling that exists in a state of indefinite potential. But the core insight is that the information isn't traveling, Pitha. The correlation is inherent to the system. So the locality isn't violated because there is no communication. There is no signal. There is no information transfer. If you understand that, if you can really feel that distinction, then the spooky part starts to fade away. It's still weird. It's still counterintuitive, but it's not magic. It's not breaking the laws of physics. It's just physics doing something we didn't expect. It's like when we discovered that light is a wave. Before that, we thought light was a stream of particles. Newton thought it was particles. And then we saw interference pattern, and we said, oh, it's a wave. And then later, we saw the photoelectric effect, and we said, oh, it's particles. And then we realized it's neither. It's a quantum field. It behaves like a wave in some conditions and like a particle in others. We were trying to force light into our categories. We were saying, is it an apple or an orange? And nature was saying, it's a fruit. Entanglement is the same. We are trying to say, is it local or non-local? And nature is saying, it's quantum. We have to expand our categories. We have to build new concepts. I think the biggest challenge for the next generation of physicists isn't solving the math. It's not about finding new equations. We have plenty of equations. We have the standard model. We have general relativity. The challenge is conceptual, and it's about building a language that can talk about these things without getting stuck in the old broken metaphors. We need a new way to think about space, time, and matter. We need a way to talk about the world that doesn't depend on our limited macroscopic experience. And that is where you come in. Yet you, the student, you, the curious mind, you have a fresh start. You aren't burdened by the baggage of the last 50 years. You can look at the data with new eyes. You can challenge the assumptions. Don't listen to the experts. Or don't listen to me. Don't listen to the textbooks. Read the textbooks to learn the techniques, to learn the math. But question the interpretation. Ask why. Ask what if. And don't be afraid to look foolish. The most important discoveries come from asking the question that everyone else thinks is too simple or too weird or too stupid. The history of physics is full of people who were told their ideas were crazy. Einstein, Bohr, Heisenberg. They were all considered radicals. They were all fighting against the establishment. So be a radical, be a nuisance, be a pain in the neck, but be honest, follow the evidence, and don't settle for shut up and calculate. Because the goal is not to calculate. The goal is to understand. And if we never fully understand, well, that's okay too. We can still appreciate the beauty of the system, and we can still marvel at the way the universe manages to be both chaotic and orderly, both local and entangled, both simple and complex. That is the true nature of science. It's an adventure. It's an ongoing process. It's not a destination. I want to leave you with this thought. We are part of this system. We are made of atoms, and those atoms are quantum, and they are entangled with the rest of the universe. We are not observers standing outside the universe looking in. We are participants. We are the universe observing itself. And maybe, just maybe, the reason the universe is so weird is because it's trying to tell us something. It's trying to tell us that we are part of a much larger, much more interconnected whole than we ever realized. It's a humbling thought. It makes you feel small, but it also makes you feel connected. You are not a solitary observer. You are a piece of the puzzle. And the puzzle is connected, part to part, from the smallest particle to the farthest star. And that is a beautiful way to think about your place in the cosmos. I have spent my whole life playing with these ideas. I have spent my whole life trying to push the boundaries of what we know, and I'm still here, still curious, still wondering, because that's the best part. The wondering, the not knowing, the feeling that there is always something more to discover. So keep wondering, keep asking, keep looking for the answer, even if you never find it, because the search itself is worth it. Let's think about the future. Quantum computing, quantum cryptography, quantum teleportation. These are the practical applications of entanglement. We are moving from the era of understanding to the era of application. We are learning how to harness these quantum correlations to perform tasks that were impossible before. We are building machines that use entanglement to compute faster, to communicate more securely, to simulate the behavior of molecules. We are becoming masters of the quantum world. And as we do that, as we build these tools, we will learn more about the underlying physics. We will refine our understanding. We will push the boundaries further. It's a cycle. You build a tool, you learn from it. You use what you learn to build a better tool. It's the cycle of science. It's the engine of progress. And we are just at the beginning. We are like the early aviators building gliders, trying to figure out how to fly. We have barely scratched the surface of what's possible with quantum technology. The next 100 years will be incredible. We will see things that we can't even imagine today. We will solve problems that we haven't even identified yet. And it all starts here. It all starts with the question. It all starts with the curiosity. So don't lose that. Protect it, nurture it, because it is the most valuable thing you have. And remember, the world is not the way you think it is. It is much, much stranger. And that is a good thing. I have talked a lot about the math, about the experiments, about the history. But I want to close by talking about the feeling of discovery. That moment when you see something for the first time, when you understand something that was hidden from you before. That rush, that excitement, that joy, that is what it's all about. That is why we do physics. It's not for the prizes. It's not for the fame. It's for that moment, that fleeting, beautiful moment of clarity. And if you can experience that, if you can feel that, then you have succeeded. You have touched the truth. You have connected with the universe in a way that very few people ever get to. So go out there and find your own discoveries. Go out there and ask your own question. Go out there and be curious. Because the universe is waiting for you. The universe is waiting to be understood, and you are the one to do it. I look at the blackboard and I see the chalk dust. I see the equations. I see the math. And I love it. It's beautiful. It's human. It's our best attempt to describe the reality of the situation. It's not perfect. It's not complete. But it's our attempt. And that is enough. We are just trying to read the book of nature. And some chapters are harder than others. Entanglement is one of the hardest. But it's also the most rewarding. It teaches us about the interconnectedness of things. It teaches us about the unity of nature. It teaches us that there is a deep underlying harmony in the universe, even if we don't always see it. So don't get frustrated. Don't give up. Keep looking for the pattern. Keep looking for the harmony. It's there. You just have to look hard enough. And maybe one day you'll be the one to solve it. You'll be the one to write the next chapter. You'll be the one to tell us what it all means. That is my hope for you. That is my challenge to you. Go out there and change the world. Go out there and make your own mark. And remember, the journey is the reward. I've had a good run. I've enjoyed every minute of it. I've chased the mysteries. I've broken the locks. I've played the drums. I've lived a full life. And I've tried to share that with you. I've tried to give you a glimpse of the wonder I felt. I hope I've succeeded. I hope I've sparked something in you. I hope I've made you see the world a little differently, because that is the best I can hope for. I have enjoyed this lecture. I have enjoyed this time with you. It's been a pleasure to share these thoughts, these memories, these questions. And now it's time to go. It's time for you to continue the work. It's time for you to take the torch and carry it forward. The future is yours. The mystery is yours. The universe is yours. Go and explore it. Go and understand it. Go and love it. Because it is a wonderful, strange, beautiful, and mysterious place, and you are lucky to be a part of it. I have no more to say. I have said all I can. The rest is up to you. Thank you for listening. Today's lecture is about the man who broke reality, how Niels Bohr changed physics forever. I want you to think about how we usually describe the world as you got a rock, you got a tree, you got the earth spinning on its axis. We grow up with this picture. It's a very clean picture. If things move from one place to another, they have a path. If I throw a ball, I can tell you where it is, how fast it's going, and exactly where it will land if I know how hard I pushed it. That's what we call classical physics. It's comfortable. It makes sense. It's intuitive. But then we look closer. We look at the tiny bits that make up the rock, the tree, the ball. We look at the atom, and suddenly the rules change. They don't just shift a little bit, they break. And there was this guy, Niels Bohr, sitting in Copenhagen, who started the whole mess. Not because he wanted to break things, but because he couldn't stand it when the math didn't match what we saw in the lab. Let's go back to the early 1900s. People thought they had physics figured out. They really did. They had Maxwell's equations for light and electricity, and they had Newton for the motion of planets, and everything looked like a finished building. Just a few minor details left to sweep up, like why certain gases glowed in specific colors when you zapped them with electricity. That's it. Just some housekeeping. But that housekeeping was actually the cracking of the foundation. Think about hydrogen. It's the simplest thing in the universe. One proton, one electron. If you put gas in a tube and heat it up, it glows. But it doesn't glow with a rainbow. It glows with specific lines. Red, blue, green, violet. Why? If the electron were like a little planet orbiting the sun, it should be able to orbit at any distance. You could push it a little further out or a little closer in. The energy should be continuous. You could have any color you wanted, depending on the speed of the electron. But the light from hydrogen didn't care about that. It only showed specific lines. It was as if the electron could only stand on certain steps of a ladder and nowhere in between. Bohr wasn't the first to think about quantization. Planck had played with the idea for heat, and Einstein had used it for light. But Bohr did something stranger. He looked at that hydrogen atom and he said, okay, let's assume the electron can't just be anywhere. He just declared it. He put down the rule. Angular momentum is quantized. Now, why would he do that? Because the math worked. That's the part that bothers people. Bohr didn't have a deep underlying mechanism for why the electron couldn't be in the middle of the steps. He just looked at the patterns in the light, the Balmer series, the Lyman series, and he saw the structure in the number. He built a model that fit the data, even if it defied everything we knew about how moving charges behave. You see, classical electricity, Maxwell's stuff, says that if you have a charged particle, like an electron moving in a circle, it's accelerating. And an accelerating charge radiates energy. It's just what it does. It's like shaking a charged rubber duck. You get ripples in the electric field, which carries energy away. If the electron radiates energy, it should lose speed. If it loses speed, it should spiral into the center. The atom should collapse in a fraction of a second. With this, everything should collapse in your coffee cup, your chair, your skin. Everything should vanish into a hot, dense mess of nothingness if Maxwell was right. But we're still here. So Bohr had to make a choice. He either throws away Maxwell or he throws away the idea that the electron is moving like a planet. He decided to keep Maxwell for light, but ignore it for the atom. He said, let's assume the electron stays in a stationary state without radiating. It's bold. It's a bit crazy. And it worked. I remember thinking about this for a long time. It feels like cheating. You would define a rule that says that this thing doesn't follow the laws of physics, and suddenly the experiment matches your calculation. It's like saying, the bridge won't fall down because I forbid it to fall. But that's what Bohr did. He forced the atom into a configuration that produced the right light spectrum. Let's talk about that transition, the jump. When an electron goes from a high energy orbit to a low one, it emits light. It's not a continuous slide. It's a jump. One moment it's here, the next it's there, and the energy difference comes out as a photon. We call it a quantum leap, which is a terrible term because it sounds huge, but it's actually a very precise, very tiny thing. It happens instantaneously. The physics community was confused. How does it get from one to the other without passing through the space in between? What does it do while it's jumping? Bohr didn't have the answer. He just said, don't ask that. He treated the atom as a set of rules, a calculation device, rather than a visualizable machine. This is where the trouble with Bohr starts. If you're a guy like me who likes to visualize gears and levers, and Bohr wasn't interested in the what is it really doing question. He was interested in the what can we say about it question. He developed this idea called complementarity. You've probably heard of the wave-particle duality, huh? Light can look like a wave. You see interference patterns when you shine it through two slits. It can look like a particle. It knocks electrons off a metal plate in the photoelectric effect. And Bohr looked at this and said, look, you can't have both at the same time. He wasn't saying the universe is confused. He was saying, we are limited. The experiment you choose determines the nature of the reality you see. If you set up a screen to catch waves, you get waves. If you set up a detector to catch particles, you get particles. You can't ask the electrons, are you a wave or a particle? Because that's the wrong question. The electron doesn't care about your labels. It's like looking at a cylinder. If you shine a light from one side, you get a rectangular shadow. Shine it from the top, you get a circle. Is the object a rectangle or a circle? It's a cylinder. The shadow depends on how you look at it. Bohr insisted that nature is like that. You get information based on your interaction with the system. You can't strip away the observer from the observation. Now, this drove Einstein absolutely mad. Einstein was a realist. He believed there was a world out there independent of us with definite properties. He wanted to know If I'm not looking at the moon, is it still there? He thought quantum mechanics was incomplete. He thought there were hidden variables that would explain the randomness. He kept saying God does not play dice with the universe, and Bohr famously would just tell him, "Stop telling God what to do." They went at it for years. Solvay conferences, debates, letters. Einstein would come up with a thought experiment, a gotcha moment, where he'd try to trap the quantum rules in a logical contradiction. He'd say, aha, if we measure the momentum here, we should know the position there, but the uncertainty principle says we can't. So the theory must be wrong. And Bohr would go away, scratch his head, think about it overnight, and come back the next day with a solution that showed Einstein had missed something. Bohr would point out that, wait a minute, the measuring device itself has mass, and the interaction of that device with the particle creates the uncertainty you're trying to avoid. It was a beautiful duel. Two of the smartest people in history arguing about the nature of reality, and Bohr won. Not because he was smarter, Einstein was Einstein, but because the math of quantum mechanics was just too damn robust. It kept working. Every time they tested it, the predictions held up. Let's get into the mechanics of that uncertainty. Why couldn't they win? Think about trying to look at a bug on a leaf. To see the bug, you have to bounce light off it. But if the bug is tiny, you need a high energy, short wavelength light. That light has enough energy to kick the bug right off the leaf. So by the act of observing, you change the thing you're looking at. Now, in the classical world, you can make the light dimmer, use a different frequency, minimize the kick. But in the quantum world, there's a limiter. There's a minimum amount of interaction, a quantum of action. You can't interact with less than that. So there is an inherent, irreducible change you make to the system when you look at it. Bohr realized this wasn't a technical failure of our microscope. It was a property of the universe. So where does that leave us? It leaves us with a reality that isn't solid. It's probabilistic, that we don't say the electron is here. We say the probability of finding the electron here is high. It's all about odd. It's like a casino, but the house rules are written in the fabric of space. Bohr didn't solve the mystery of what's happening behind the scenes. He just told us to stop asking. He convinced a whole generation of physicists to accept that the math is the reality. Shut up and calculate. I don't think he said that exact phrase, but that was the vibe of the Copenhagen interpretation. Focus on what you can measure and don't lose sleep over the rest. I struggled with this. I spent a lot of time trying to build models, little pictures that make sense of the math. I wanted to see the electron. I wanted to see the path. But Bohr's way of thinking, this focus on the act of measurement, it was useful. It allowed us to build the transistor, to understand chemistry, to build the BOMB, to do all the things we do now. It worked. And in physics, if a theory works, you respect it, even if it feels wrong in your gut. Let's look closer at the specific moment when he stood up to the establishment. Before Bohr, the scientific method was about objective detachment. You are the scientist. The thing you study is the object. You keep your distance. You measure it. Bohr said, no, that's not possible. Imagine you're trying to study the wind. You hold up a wind vane. The vane interacts with the wind. The wind pushes the vane. You are changing the wind by measuring it. Bohr took that simple idea and realized it's true for everything, even at the smallest scale. He understood that our language itself is based on classical experiences. We have words like position and velocity because we live in a world of macroscopic objects. We don't have good words for what happens inside an atom with F. So when we try to talk about it, we get confused. He famously suggested that maybe the reason we have these paradoxes is that our language is too limited. We are like prisoners trying to describe the sun by only using words for darkness. It's an honest admission of limitation. That's what I liked about him. He didn't try to be a philosopher king. He was a physicist who dealt with the mess of experimental data. He had that institute in Copenhagen It was a gathering place, and he'd have people like Heisenberg, Pauli, Dirac, the whole crew. They'd sit around drinking tea, smoking pipes, arguing, writing equations on chalkboards until they were exhausted. He was the conductor. He wasn't always the one solving the differential equations. Sometimes he'd get someone else to do the heavy lifting. But he was the one who kept the vision clear. He'd ask, but does that make sense? Is that what the data says? One of the things he pushed for was the correspondence principle. This is a very logical idea. He said, look, quantum mechanics is weird, but it has to turn into classical physics when things get big. If you have an atom with 1 billion electrons, it should behave like a little classical ball. The quantum effects should wash out. If your new theory doesn't recover the old correct theories at the limit of large numbers, then your new theory is wrong. That's a brilliant way to police your ideas. It kept them grounded. It forced the radical, strange quantum math to respect the Newtonian world we see every day. It was his bridge between the two realities. And yet his work during the Second World War was something else entirely. He was in Copenhagen when the Nazis came. He had to smuggle his Nobel medal out. He dissolved it in acid to hide it, then precipitated it back out later. He knew the potential of what they had discovered. He knew about the energy in the nucleus. He was terrified of what would happen if that knowledge was used for weapons. He tried to talk to Churchill, to Roosevelt. He was trying to warn them about the dangers of an arms race. He wasn't just a professor in a lab. He was a man who realized the world had changed because of his work. He saw the atom as both a scientific mystery and a geopolitical threat. That's a burden. Most physicists just want to solve the problem and go home. Bohr had to live with the reality of the genie he helped let out of the bottle. Let's come back to his actual day-to-day life at the Institute. It wasn't just formal lectures. It was a constant conversation. People would go for walks with him. He'd talk. He was known for being a bit difficult to follow sometimes. He didn't speak in clean, bullet-pointed sentences. He spoke in circles, trying to pin down the elusive nature of the truth. He'd pause and mutter, correct himself. No, that's not quite right. And maybe if we consider, that's how real science is done. It's not a polished presentation. It's a messy, chaotic process of figuring out where you're wrong. And Bohr encouraged that. He wanted people to challenge it. He wanted the best minds to poke holes in his ideas because that's how you find out if they're solid. Think about the structure of an atom again. We have the nucleus in the center, the heavy stuff, and the electrons buzzing around in clouds or orbitals. Now, we don't think of them as orbits in the sense of a planet going around a sun. We think of them as probability distribution. That shift from path to probability is Bohr's ghost. He's the one who planted that seed. If you don't accept that shift, you're stuck in the 19th century. You're trying to use gears to explain a cloud, and it won't work. You have to let go of the need to visualize the path. That's the hardest thing for a student to do. I see it all the time. Students come into the class and they want to draw a line. Where does the electron go? And I have to tell them it doesn't go anywhere. It exists as a state. It's not satisfying. It doesn't give you a warm, fuzzy feeling of understanding. But it's the truth of how the universe operates. Now, let's explore why this matters beyond the classroom. Bohr's philosophy of complementarity, this idea that we define what we measure, has seeped into other areas. It changes how we think about information. If you try to measure everything at once, you destroy the information. You have to sacrifice one thing to know the other. That's not just quantum mechanics, that's a constraint of the universe. It's like trying to perfectly map a city. If you make the map too detailed, it becomes the size of the city. You lose the utility of the map. You have to pick what's important. You have to decide what you're looking for before you start the measurement. Bohr didn't just teach us about atoms. He taught us about the limits of human inquiry. Let's pause for a second. Is there anything he got wrong? He was stubborn. He didn't like some of the later developments, like the idea of the cat thought experiment, Schrödinger's cat. He thought it was silly to take the math so literally that you ended up with a dead and alive animal. He wanted to keep the focus on the experimental outcome, not the philosophical paradox. But perhaps he was too dismissive of the paradoxes. Maybe those paradoxes were trying to tell us something deeper about entanglement, about how pieces of the universe stay connected in ways we don't fully grasp. He died in 1962. By then, the world was completely different. We had nuclear power, we had electronics, we had a fundamental understanding of matter that started with his hydrogen atom model. I often think about that transition. How did a guy in the early 20th century with simple tools see so clearly what everyone else was missing? He didn't have computers. He didn't have high-energy particle accelerators. He had a pencil paper and the stubborn refusal to accept the classical status quo. He had intuition. He had a physical feel for the problem. He knew that the Balmer formula wasn't just a coincidence. He knew that nature had a reason for those specific lines. That intuition is the most important tool a physicist has. You can have all the math in the world, but if you don't have the nose for where the truth is, you're just pushing symbols around. Let's break down the logic of his most famous contribution one more time, just to be sure we have it. The old model, Rutherford atom, a positive nucleus, a negative electron. The problem, radiation. The electron should spiral into the Bohr fix, quantization. The electron is restricted to specific energy level. The constraint, no emission of radiation while in these states. The jump, radiation only happens during the transition between states. The result matches the spectral lines perfectly. It's elegant, it's simple, it's completely wrong in terms of the orbit visualization. We know now that the electron isn't a little ball on a track, but it was the necessary step to get to the truth. You don't get to the quantum mechanical cloud without the Bohr atom. It's like a ladder. You need the rungs to get to the roof. You don't stay on the ladder forever, but you need it to get up there. I suspect that's how all progress happens. We build these wrong models that are right enough to get us to the next level. We hold on to them as long as we can, until the next guy comes along and shows us that our ladder was just the first part of the climb. Bohr wasn't afraid of being wrong. He was afraid of being irrelevant. He wanted to be at the center of the action, asking the hard questions, and that's what I admire most. Think about the debates with Einstein again. Einstein was the heavyweight champion. He had the weight of intuition, the weight of the classical world, the weight of a genius who had already changed everything once before. And Bohr was the challenger, the guy from the smaller pond, pushing a weird, probabilistic view of reality. Einstein wanted a universe of clockwork. Bohr wanted a universe of potential. Who was right? Well, the evidence is in the universe is weird. It's probabilistic, people call it. It's entangled. It's not clockwork. Bohr won the argument because the universe turned out to be the way he described it, not the way Einstein wanted it to be. That's a hard lesson, but you can be the smartest person in the room. You can have the most beautiful philosophical arguments, but the universe doesn't care about your aesthetics. It doesn't care if you like the idea of God playing dice. It does what it does. Bohr's life was a testament to that humility. He was a humble man in the face of the unknown. He didn't claim to know the mind of God. He just claimed to know how to calculate the spectra of hydrogen. And that turned out to be enough. Now let's look at the complementarity idea again, because it's the one thing people consistently misunderstand. They think it means everything is relative. It doesn't. It means everything is contextual, that there is a difference. But relativity says the speed of light is constant. Complementarity says the observation is dependent on the experimental arrangement. It's a statement about our interaction with nature, not about the moral decay of truth. If you change the experimental arrangement, you change the nature of what you see. That's a physical fact, not a philosophical stance. Imagine you're trying to measure the temperature of a gas. And what if you stick a thermometer in? The thermometer takes heat from the gas and see. The gas cools down and you've changed the temperature. Now, in a large container, that effect is tiny. It's negligible. But in a small container, it's huge. It dominates the measurement. Bohr understood this. He understood that the measuring device and the thing being measured are one system. You can't divide them. And that realization that we are inside the system we are trying to observe, that's the real shift. That's the paradigm shift, if you want to use that term, though I hate it. It's a shift in perspective. It's a shift from outside observer to participant. We are participants in the universe. We aren't just watching it from the bleachers. Does this mean everything is subjective? No. The results of the experiments are objective. Anyone can repeat them. If I measure the spectral lines of hydrogen, I get the same numbers you do. The interpretation of those numbers is where the strangeness lies. The numbers themselves are hard, cold facts. Bohr loved the numbers. He was a calculator. He kept pushing the math, kept refining the models. He wasn't satisfied with a vague idea. He wanted the numbers to match. Let's consider the transition to the later part of his life. After the atomic work, he spent a lot of time thinking about openness. He wrote letters to the United Nations. He advocated for transparency. He believed that the power of the atom was so great that it required a new way of thinking about international relations. He thought that if we knew how dangerous the technology was, we would be forced to cooperate. He was an optimist about human nature in a way that seems almost naive today. He thought that knowledge would lead to wisdom. He thought that if we understood the physics, we would understand the stakes. Did he succeed there? No, we have more BOMBs, more tension, and not enough openness. But the fact that he tried, the fact that he carried that weight, says something about the man. He wasn't just a physicist, he was a citizen of the world who understood the magnitude of his contribution. I remember reading his papers. They aren't the cleanest papers. They're rambling, they're dense, and we struggle to find the words. He was trying to express something that didn't have words yet. He was inventing the language as he went along. That's why his writing is so difficult. You're reading the thoughts of someone who is building a structure in the dark, and you have to be careful when you read them. Well, you can't just cherry pick a quote. You have to understand the context in order. You have to see the struggle. One thing he famously said, and I'm paraphrasing here, is that the opposite of a profound truth may well be another profound truth. That sounds like a contradiction. How can two truths be opposite? Think of the wave-particle dualities. The statement light is a wave is a profound truth. The statement light is a particle is a profound truth. They seem opposite, but they are both true depending on how you look. That's the kind of thinking Bohr cultivated. He taught us to hold two contradictory ideas in our heads at the same time and not panic. He taught us to embrace the paradox. Most people run from paradoxes. They want a clean answer. They want to know, is it this or is it that? Bohr says it's both, and the fact that you see it as a paradox is a reflection of your own limited understanding, not the universe's. That's a powerful lesson. It applies to everything. If you see a contradiction in your life, in your politics, in your relationships, don't rush to resolve it. Sit with it. Maybe both sides of the contradiction are true. Maybe you're looking at a slice of a larger, more complex whole. Bohr didn't come to this easily. He had to fight for it. He had to be the guy who stood up to the classical giants and said, "You're wrong. The world is weirder than you think." Let's talk about his background a bit more. He wasn't some outsider. He was Danish. He was part of the European academic establishment, but he had a different perspective. He was a practical man. He liked football. He was a good goalkeeper. He understood that you have to be ready to react, to jump in the right direction, to make the save. Physics was like that for him. You have to be ready for the curveball. He grew up with a father who was a physiologist. He was surrounded by science. He learned to observe, to experiment, to think about the physical mechanisms of life. That groundedness never left him. Even when he was doing the most abstract quantum mechanics, he was thinking about the physical reality. He wanted to know what the electron was doing. He wanted to know how the atom worked. He wasn't a mathematician who played with symbols in a vacuum. He was a physicist who tried to map the territory. And when he got stuck, he didn't give up. He reached out. He invited people. He made his institute a hub. He created a community. That's something we often forget. Science is not a solo act. It's a conversation. It's a long, centuries-long conversation that we all participate in. Bohr was one of the greatest conversationalists of that era. Now, I want you to imagine the atmosphere in that institute in the 1920s. You've got the best minds in the world, young and hungry, tearing apart the old physics and building something new. You've got Heisenberg, who's only in his 20s, coming up with the uncertainty principle. You've got Dirac, who's coming up with antimatter. And you've got Bohr, the elder, the guy who keeps asking, is that really what you mean? It must have been electric, Lafave. The air in that room must have been heavy with ideas. That's what I love about science. It's not about the buildings or the funding or the prestige. It's about that moment of discovery, that realization that you finally understood something about the way the universe is built. And Bohr was the guy who facilitated those moments. He made the space for them. He wasn't the guy who had all the answers. He was the guy who asked the right questions. If you take one thing from this talk, let it be that the value of a question is often higher than the value of an answer. An answer ends the conversation. A question keeps it going. Now, Bohr's whole life was a question. He didn't stop until the day he died. He was always thinking about the next problem. He was always worried about the next crisis. He didn't have the luxury of sitting back and enjoying his fame. He was a restless mind. I find that comforting. It means you don't have to worry, have it all figured out. You don't have to be perfect. You just have to be curious. You have to be willing to look at the data, even if it contradicts what you believe. You have to be willing to say, I don't know, but let's find out. That's the spirit of the man who broke reality. He didn't break it because he was a vandal. He broke it because he was an explorer. He looked at the walls of the classical building and he realized they were just a paint job. Behind them, there was a vast, mysterious quantum universe waiting to be discovered. And he was the first one to walk through the door. Is there anything else we should touch on? Perhaps the atomic BOMB work in Los Alamos? He went there too. He acted as a consultant. He saw the enormity of the project. He saw the tension between the military need for secrecy and the scientific need for openness. He felt that tension deeply. He wasn't involved in the technical details of building the BOMB. That was Oppenheimer and the others. But he was involved in the moral weight of it. He was a conscience for the project. He reminded them that they were dealing with the fundamental forces of nature, and that those forces belonged to humanity, not to a single government. He didn't get his way. History took a different turn, but the point is that he stood up, he spoke, he used his influence for something beyond physics. That's a full life. That's a life that had an impact. I keep coming back to his personality. He was modest, yet commanding. He was confusing, yet brilliant. He was a puzzle. And maybe that's the point. If you want to understand the man who spent his life studying the fundamental puzzles of the universe, you have to accept that he too was a puzzle. You can't solve him. You can only observe it. What if we look at the way he taught? He didn't lecture from a podium, reading from notes. He paced, he drew, he talked, he involved everyone. He made you think. Hey, that's the only way to teach physics. You can't learn physics by reading a textbook. You have to do it. You have to wrestle with the problem, but you have to try to solve them, fail, and try again. Bohr knew that. He made his students do the work. I think that's why his influence lasted. It wasn't just his papers, it was the people he trained. They went out into the world and taught others, and they carried his spirit, that skepticism, that curiosity, that refusal to accept simple answers. Let's think about the way he dealt with his own uncertainty. There's a story about him having a horseshoe over his door. Someone asked him, Niels, surely you don't believe in that stuff? And he said, no, I don't believe in it, but they say it works even if you don't believe in it. That's a classic Bohr joke. It's a way of saying, look, I'm a rational guy, but the universe is weird and I'm keeping an open mind. It's also a way of deflecting the question, of showing that he didn't take himself too seriously. He knew the limitations of human knowledge. He knew that the line between science and superstition is often thinner than we'd like to admit. He didn't have all the answers. None of us do. But he had the courage to search. And in searching, he changed our reality. He shattered the classical dream and forced us to wake up in the quantum reality. And even if that reality is uncomfortable, even if it defies our intuition, it is our reality. So when you look at the stars, or the atoms in your hand, or the screen in front of you, remember Bohr, remember the guy who looked at the hydrogen atom and saw not just a simple light, but a secret about the nature of existence. Remember the guy who was willing to let go of everything he thought he knew to follow the truth where it led. It's a tough path. It's not for the faint of heart. But it's the only path that leads to understanding. Are there any loose ends? What about the measurement problem today? We still argue about it, and we still have the many worlds interpretation, the de Broglie-Bohm interpretation, the Copenhagen interpretation. We haven't settled the argument. We are still debating the nature of reality, and that's fine. That means the conversation is still alive. Bohr would have liked that. He wouldn't have wanted us to stop the debate. He would have wanted us to keep pushing, keep questioning, keep looking for the next layer of the truth. Maybe that's his greatest legacy. He left us with a job to do. He left us with a set of questions that haven't been answered yet. He left us with the unfinished business of the universe. And that's a good place to be. We have work to do. We have theories to build. We have experiments to run. We have a universe to understand. Don't be afraid of the paradoxes. Don't be afraid of the strangeness. Don't be afraid to look at something and say, that doesn't make sense. It's all. That's where the fun starts, and that's where the discovery begins. So keep thinking, keep asking, keep looking for the cracks in the foundation, because that's where the light gets in. Bohr showed us the way. He showed us that the world is more complex, more beautiful, and more mysterious than we ever imagined. And he gave us the tools, the math, the uncertainty principle, the complementarity to start to make sense of it. And now it's up to us. We have to carry that torch. We have to keep the conversation going. We have to keep pushing into the unknown. It's a great adventure, this physics thing. Yeah. And we're lucky to be part of it. And I think I've said enough. I've rambled a bit, but that's the nature of these things. You start with a simple idea, an electron in an atom, and you end up with the nature of reality itself. That's the beauty of it. It's just you and the problem. That's all there is. And that's enough. Thank you.